In the silence of an endless night, a faint whisper of light still lingers. It is the afterglow of creation, a gentle aura permeating the cosmos. Long ago, the universe was born in a blaze of brilliance. As it expanded and cooled, that blinding light faded to a dim murmur, leaving behind a soft background glow. Today, that ancient light remains all around us, a cosmic twilight that whispers of the dawn of time. This faint afterglow is everywhere, though we cannot see it with our eyes. It shines not in visible light, but in soft radio waves, a glow only detectable with special instruments. Its temperature is barely above absolute zero, just a few degrees above the coldest temperature possible. The entire universe is bathed in this subtle warmth, a remnant of the fireball that filled space billions of years ago. Even in the darkest void, this ghostly light is there, a memory of when the cosmos was young and hot. At the dawn of time, the universe was a searing ocean of energy. Space itself glowed like the surface of a star, filled with hot, dense plasma. In those first moments, light could not travel freely. It was trapped in a cosmic fog, scattered endlessly by free electrons in the fiery haze. But as the universe expanded, it began to cool. After about 380,000 years, the temperature fell enough for electrons and protons to unite into neutral atoms. The fog lifted, and space suddenly became transparent. Light that had been imprisoned was set free, streaming out in all directions. That liberating moment left an afterglow that still travels through space today. Eons passed. In the absence of any stars, the young cosmos lay in darkness, lit only by this fading afterglow. This era, a cosmic dark age, lasted for millions of years. Eventually, gravity drew matter together and kindled the first stars, bringing new light to the universe. By then, the primordial glow had cooled and dimmed to a faint whisper. The once blazing fireball's light became a gentle background murmur, waiting to be discovered by future beings. Fast forward billions of years. In the 20th century, humans built sensitive antennas to listen to the sky. In the 1960s, two astronomers detected an unusual hiss of radio noise coming from every direction. It was a persistent, gentle static that refused to go away, even after they checked their equipment and even chased pigeons from their antenna, suspecting an earthly cause. Finally, they realized this was no ordinary interference. It was the ancient echo of the Big Bang. Without knowing it at first, they had heard the universe's own birth cry, softened by time into a faint radio whisper from the depths of space. In modern times, scientists have mapped this cosmic afterglow across the entire sky. They found it to be remarkably uniform, the same soft glow everywhere, with only tiny variations in temperature. These slight ripples in the warmth are like faint patterns on a vast, calm sea. They are the imprint of the earliest structures, the seeds from which galaxies and clusters would one day grow. What we see is essentially a baby picture of the cosmos, taken long before any star or planet existed. In this image of infancy, the universe shows us its first delicate hints of structure emerging from the primordial haze. Yet, hidden in those delicate patterns is evidence of something more. The early universe's gentle afterglow contains whispers of an invisible presence. The galaxies and clusters that eventually formed could not have arisen from visible matter alone. there was simply not enough. Some additional gravity was at work, drawing matter together in the darkness. It is as though an unseen hand was sculpting the cosmic landscape from behind a curtain. This realization leads us into one of the greatest mysteries of all: dark matter, the velvet darkness that holds the cosmos in its grasp. For all the stars and galaxies we see shining in the night, there is far more out there that remains unseen. This invisible mass permeates the universe like a subtle, all-enveloping shadow. It neither emits nor reflects light, rendering it truly invisible to our eyes and telescopes. And yet, its presence is felt through the gentle tug of gravity on everything around it. This mysterious substance, dubbed dark matter, acts as a hidden scaffold for the cosmos, a silent framework holding galaxies together in its embrace. Decades ago, astronomers began noticing curious motions in the heavens that hinted at this invisible mass. In distant clusters of galaxies, the galaxies were moving too fast for the gravity of their visible stars alone to hold them together. By rights, they should have flown apart, yet something unseen was keeping them bound. Similarly, within individual galaxies, stars far from the center were orbiting at surprising speeds. In the outer reaches, where the pull of visible matter dwindled, the stars still raced along as if held tight by an invisible halo of gravity. It was as though each galaxy sat in a cocoon of hidden mass, providing the extra pull needed to keep those fast-moving stars from drifting off into space. Over time, more and more evidence piled up for this unseen influence. Light from distant objects would bend and warp as it passed massive bodies, a phenomenon known as gravitational lensing. Often, the amount of bending far exceeded what the visible matter could cause, hinting that a substantial amount of invisible mass was present. These cosmic mirages, rings and arcs of light around galaxies and clusters, revealed that something substantial, yet invisible, was warping spacetime. Everywhere we looked, the same story emerged. There wasn't enough visible matter to explain the observed gravity. An enormous amount of matter was missing to our eyes. But it was clearly there, silently influencing the motion of galaxies and the path of light itself. Today, we understand that dark matter is far more abundant than the ordinary matter we are familiar with. By the best estimates, for every pound of normal matter, there are about 5 or 6 pounds of dark matter hidden alongside it. In total, it outweighs all the stars, gas, and dust by a wide margin. We find ourselves living in a universe dominated by this unseen ingredient. The bright galaxies and glowing nebulae we observe are like foam on the crest of a deep, invisible ocean of dark matter that permeates space. It is the unseen bulk of this ocean that gave our universe the structure we see today. Dark matter played a crucial role in shaping cosmic history. In the early universe, long before the first stars ignited, dark matter began to gather into clumps under its own gravity, forming an invisible skeleton in the cosmos. Ordinary gas was drawn into the deep gravitational wells of this hidden framework. In those cradles of gravity, the gas condensed until the first stars and galaxies burst into light. The grand design of the cosmic web, with its filaments of galaxies and enormous voids, was sketched out largely by dark matter's gravity. Without that hidden scaffolding to guide matter, the universe might have remained almost featureless, and the glittering archipelago of galaxies we know might never have come to be. Yet for all we have learned about its effects, the true identity of dark matter remains elusive. It neither shines nor interacts with normal matter in any obvious way, except through gravity. Scientists have proposed many ideas to explain it. Perhaps dark matter consists of exotic particles, different from the atoms that make up stars and people, particles that rarely, if ever, collide with ordinary matter. Or maybe it is something even stranger, like numerous primordial black holes or other exotic remnants from the universe's birth. Sensitive detectors buried deep underground have been listening for the faintest collisions between dark matter particles and normal atoms, hoping to catch a rare spark of interaction. Powerful particle accelerators have been smashing particles together at high energies to see if new, hidden particles appear. So far, these efforts have come up empty-handed. Dark matter lives up to its name, invisible and undetected by our instruments. A cosmic enigma, lingering in the shadows. Between the bright filaments of galaxies that dark matter helped form, there lie cosmic voids of staggering scale. These are realms of nearly pure nothingness, vast, silent expanses where galaxies are exceedingly scarce. In these intergalactic deserts, tens of millions of light years can stretch between one galaxy and the next. Here, space is quiet and dark, an immense sea with only a few scattered islands of starlight. Such voids are among the most haunting features of our universe, colossal volumes so empty that they challenge our understanding of how nothingness can be. Astronomers were astonished when they discovered the first truly immense void in the 1980s, in the direction of the constellation Boötes. This great nothing, as it was informally called, spans hundreds of millions of light years with almost no galaxies inside. It is so vast and so empty that if our Milky Way lay at its center, we might have never realized other galaxies existed until we developed powerful telescopes. The night sky would be nearly devoid of any visible galaxies. The few galaxies that do lie at the edges of the Boötes void form a distant shell around a tremendous volume of darkness, like a sphere of stars enclosing a gargantuan bubble of nearly complete emptiness. Where did these giant voids come from? In the early universe, matter was spread almost evenly, like a smooth mist. But over time, gravity drew material into denser clumps, the seeds of galaxies and clusters. As those rich regions grew heavier with stars and gas, the surrounding sparse zones were left ever more empty, drained of matter. Bit by bit, small gaps widened into immense chasms. The cosmos transformed from a nearly uniform expanse into a structure with a vivid contrast. A vast cosmic foam of existence, where huge bubble-like voids are separated by filaments and walls of galaxies. Gravity and time together sculpted a universe that went from smooth to holy. Even now, as the universe continues to expand, these voids stretch wider, pushing galaxies further apart and deepening the darkness between them. Though we call them voids, these enormous cavities are not absolutely empty. Even in nothingness, there is a whisper of something. A few stray galaxies may wander inside, often small, faint dwarf galaxies, marooned in isolation. Wisps of tenuous gas drift through, and dark matter too is present, spread thinly across the emptiness. But by cosmic standards, these regions are as close to pure nothingness as nature allows. The scarcity of matter is extreme. Almost all of a void is empty darkness, so that any lone star or galaxy within it becomes an exceptional beacon, a solitary light in a vast sea of black. In these silent reaches, one might imagine that nothing ever happens. Yet even across such emptiness, signals can cross the darkness. Every so often, a sudden flash of radio waves washes over Earth from the depths of space, lasting only a tiny fraction of a second. These are fast radio bursts, mysterious, millisecond-long blazes of radio energy that flicker through the cosmic night and then disappear. They are like ghostly whispers echoing across the universe, here and gone in the blink of an eye, leaving us astonished and perplexed. Fast radio bursts, or FRBs, were only discovered in recent years, and they quickly became one of astronomy's great enigmas. The first known FRB was found almost by accident a little over a decade ago. An astronomer sifting through old telescope data stumbled upon a single, strong pulse of radio waves that had no obvious origin and lasted just a few milliseconds. It appeared out of nowhere in the recording, then never repeated. When this finding was announced, it was met with both excitement and skepticism. Could such a powerful, brief flash really come from space, or was it a fluke of our instruments? Before long, additional fast radio bursts were detected, proving that the first was not a fluke. Dozens of FRBs have now been observed all across the sky. Each burst arrives suddenly without warning, shines fiercely in radio frequencies for a split second, and then fades into silence. Often they are so brief that by the time a telescope is alerted and turns to look, the event is already over. These bursts seem to originate billions of light years away, far outside our Milky Way, implying that whatever produces them releases an almost unimaginable amount of energy in a very short time. A typical fast radio burst can, in a few milliseconds, unleash as much energy as our sun emits in many years. Most fast radio bursts have been observed only once from their source, which makes them especially hard to study. They pop up at random and vanish, leaving only a tantalizing trace in the data. But a few of these bursts have been caught repeating. One particular FRB astonished astronomers by flaring again and again, irregularly, but from the same location in the sky. This gave researchers a chance to point more instruments at it and gather clues. They eventually pinpointed its origin, a tiny, faint galaxy about 3 billion light-years from Earth. This was a breakthrough. It linked a fast radio burst to a specific galactic home, suggesting such bursts can come from small, perhaps young galaxies. Another fast radio burst provided a different surprise. It was observed to pulse with a regular pattern for a short period, almost like a heartbeat echoing from across the cosmos. For a few seconds, this FRB sent out a brief burst of radio waves every couple of 100 milliseconds, thump, thump, thumping in a steady rhythm before stopping. That steady cadence was unlike the random flashes seen before and hinted that the source might be something like a spinning neutron star, intermittently beaming radio energy toward us like a lighthouse. These rare, repeating and rhythmic bursts are precious to scientists. They offer important clues about what could be driving such extreme signals. They suggest that, at least in some cases, fast radio bursts might be linked to exotic objects that have some form of rotation or oscillation. Even with these hints, the true causes of fast radio bursts remain shrouded in mystery. One leading idea is that many FRBs are generated by magnetars, a type of neutron star with an ultra-strong magnetic field. Neutron stars are the dense remnants of exploded stars, and magnetars are the most extreme of them, capable of sudden, violent flare-ups. Magnetars occasionally release tremendous bursts of energy in the form of high-energy radiation, and it's plausible that sometimes they produce a burst of radio waves just as intense. In fact, in the year 2020, astronomers made a landmark observation, a fast radio burst originating from within our own Milky Way galaxy. They were able to trace it to a known magnetar, a dead star with a magnetic field so intense it could strip the information off a credit card from 100,000 kilometers away. This was the first direct evidence connecting magnetars with fast radio bursts. It suggested that at least some FRBs are indeed powered by these cosmic magnetic monsters. Still, magnetars might not account for every FRB that has been observed, especially the ones that occur only once and never repeat. Other cataclysms could be at play. Some scientists speculate that a one-off fast radio burst might be the dying scream of two neutron stars crashing into each other, or a star collapsing into a black hole, singular events that release a sudden jolt of energy. There are even more exotic hypotheses, from cosmic strings vibrating in space to far-fetched ideas of alien starships, though these last notions are on the fringe and lack evidence. For now, fast radio bursts remain one of the most tantalizing cosmic riddles. They are ghostly whispers from the darkness, hinting at phenomenally powerful processes we have yet to fully understand. With each new detection, we listen carefully, hoping to catch more of what they're saying about our mysterious universe. As astronomers strained their ears to catch these brief radio whispers, the universe was also preparing to speak to us in an entirely new way. For centuries, everything we knew about the cosmos came from light, visible light, or invisible forms, like radio waves, X-rays, and so on. But in recent years, we've opened our minds to a different kind of cosmic messenger, one that doesn't travel as light at all. In a quiet moment in 2015, the universe's silence was broken by a faint ripple that was not a sound in air, nor a flash of light, but a quiver in the fabric of space-time itself. We had detected gravitational waves, the subtle tremors of space and time produced by distant cosmic catastrophes. A gravitational wave is like the ripple that spreads across a pond when a stone is dropped, except the pond in this case is the very fabric of space-time. When massive objects accelerate, for example, when two black holes swirl around each other and collide, they send out waves that stretch and squeeze the shape of space as they pass by. These waves travel outward at the speed of light, carrying energy and information about the events that created them. Albert Einstein's theory of general relativity, formulated over a century ago, predicted the existence of gravitational waves. Einstein himself suspected humanity might never be able to detect such waves, because by the time they reach us from distant galaxies, their effect is unbelievably tiny. Space might stretch and contract by a fraction of an atomic diameter, far too small to notice with any ordinary measure. For decades, inspired scientists refused to be daunted by the smallness of the effect. They built huge, extremely sensitive instruments to try to listen for these ripples in space-time. Using lasers, mirrors, and long tunnels, they attempted to measure minuscule changes in distance as a gravitational wave passed through Earth. The challenge was immense. It's like trying to detect a change in the distance between the Earth and the Sun, as small as the width of a human hair. Many thought it was almost impossible. For years, the detectors heard nothing but silence and the hum of local noise. But on September 14th, 2015, in the quiet early morning hours, a very faint signal arrived, and the universe's gravitational whisper was finally heard. What the instruments detected was the merger of two black holes in a galaxy over 1 billion light-years away. These black holes, each roughly 30 times the mass of our Sun, had been orbiting each other, drawing closer and faster until they violently coalesced into one larger black hole. In that final fraction of a second, a tremendous amount of energy was released in the form of gravitational waves, energy equivalent to several suns being converted entirely into the motion of space. The ripple expanded through the universe, growing ever weaker as it spread. By the time it reached Earth, it was an almost undetectable quiver. Yet our detectors were sensitive enough to feel it. For just a brief moment, space-time in our vicinity stretched and compressed by a tiny amount. Mirrors suspended in vacuum shifted by less than the width of a proton, but it was enough. The lasers recorded the change, and a computer plot traced out a distinctive chirp-like signal. In that moment, humanity effectively grew ears to hear the cosmos. We had heard the distant crash of black holes merging, a sound not carried by air or light, but by space itself. The detection of gravitational waves was a milestone in science, confirming a major prediction of Einstein's theory and opening a new window on the universe. Astronomers around the world were elated. We had a brand new sense, a new way to observe the otherwise invisible. In the years since that first discovery, many more gravitational wave events have been recorded. We have eavesdropped on dozens of collisions between black holes, each one sending its own faint tremor through the cosmos. We've also detected the ripples from collisions of neutron stars, super-dense stellar remnants, which added even more to the story. In August 2017, gravitational wave detectors sensed a new kind of event. 2 neutron stars spiraling into each other. Unlike merging black holes, which are essentially dark and invisible except for their gravitational waves, colliding neutron stars were expected to produce a flash of light. And indeed they did. Moments after the gravitational waves were detected, telescopes caught the glow of a tremendous explosion in a distant galaxy. This was the first time we observed the same cosmic event in both gravitational waves and traditional light. The 2 neutron stars crashed and merged, emitting gravitational waves that told us about their masses and orbits, and a burst of gamma rays, followed by a glow of expelled matter that telescopes could study for days. From that single event, scientists learned that such stellar mergers are a source of some of the heavy elements in the universe. The gold in jewelry, or the iodine in our bodies, may well have been forged in the fires of merging neutron stars. It was a beautiful example of how gravitational wave astronomy complements what we can see with light, each adding piece of the puzzle to understand cosmic phenomena. Gravitational wave astronomy is still young. The detectors we have, the likes of LIGO and Virgo on Earth, are growing more sensitive, and plans are underway for space-based detectors that could catch lower frequency waves from even more massive events. In the future, we hope to hear the gentle hum of supermassive black holes merging in distant galactic cores, or perhaps the faint rolling thunder of a stellar collapse on the far side of the universe. We might even detect an almost imperceptible background of gravitational waves, a kind of space-time memory from the Big Bang itself ringing across the eons. Each new detection will teach us something new, tuning our ears to the cosmic symphony that has been playing since the dawn of time. So far, we have considered cosmic whispers carried by various kinds of waves. Light waves we can see or not see, radio waves, X-rays, and even ripples in space-time. But the universe also sends us messengers in the form of actual matter, tiny particles traveling across unimaginable distances. We live at the bottom of a vast and invisible rain of particles from space. Among these are cosmic rays and neutrinos, minute, fast-moving particles that come flying to Earth from the depths of the cosmos. They are like an aurora of particles, an ever-present but hidden glow that paints our world with information from distant stars and cataclysms. The story of cosmic rays begins with a simple question asked over a century ago. Where does the natural radiation around us come from? In 1912, an adventurous physicist took instruments up in a hot air balloon to measure radiation high in the atmosphere. To his surprise, as he ascended, the levels of radiation increased rather than decreased. This meant that some energetic radiation was coming from above, from space itself, rather than only from the ground. He had discovered cosmic rays. Though he did not know exactly what they were, he proved that Earth is constantly bombarded by something from the cosmos, We now know that cosmic rays are mostly subatomic particles, primarily protons, the nuclei of hydrogen atoms, hurtling through space at near light speeds. There are also heavier atomic nuclei among them, and a smattering of electrons and other particles. These particles are accelerated to high energies by astrophysical processes. When cosmic rays reach Earth, they usually don't make it to the surface intact. Instead, they slam into atoms in the upper atmosphere. Each such collision creates an avalanche of secondary particles that cascade down through the atmosphere. Imagine a single proton from a distant star striking an air molecule 30 miles above us, unleashing a shower of hundreds of other particles that spread downward like an invisible, fleeting fireworks display. By the time the shower reaches the ground, only a few muons and other particles might remain, sprinkling through us harmlessly. We live in the middle of this constant, subtle particle rain, without noticing it, shielded by our atmosphere. Where do these energetic cosmic rays come from? Many of them are born in the deaths of stars. When a massive star explodes as a supernova, the shockwave from the blast can accelerate charged particles to enormous speeds. These accelerated particles become cosmic rays that wander the galaxy. Our Sun, during solar flares, also hurls out energetic particles, but the most powerful cosmic rays far exceed the Sun's modest storms. Some cosmic rays come from even more violent realms, perhaps the turbulent neighborhoods around supermassive black holes in distant galaxies, or the fast-spinning remnants of supernovae known as pulsars. Whenever we detect a cosmic ray of extreme energy, we are seeing evidence of a colossal accelerator out there in the universe. On rare occasions, we catch cosmic rays so energetic that they defy belief. Scientists once detected a single proton with an energy so high it was comparable to a baseball thrown at highway speed. All that energy packed into something infinitesimally small. They nicknamed it the "oh my god" particle, a tongue-in-cheek reflection of astonishment. To accelerate a proton to that speed, somewhere in the universe there must be an engine of incredible power. It could be colliding galaxies, or a supermassive black hole's jet, or some other extreme event. We still don't know for sure what launched that proton on its journey. It arrived as a messenger, telling us that nature's accelerators far surpass anything we have built on Earth. Each ultra-high-energy cosmic ray is a clue, challenging us to find its source among the cosmic giants. While cosmic rays crash into our atmosphere to announce their presence, another kind of particle messenger slips by almost undetected: the neutrino. Neutrinos are often called ghost particles because they interact with matter so rarely that they pass through entire planets as if they were not even there. Produced in copious amounts in nuclear reactions, neutrinos stream out of the cores of stars, out of exploding supernovae, out of the fusion reactions in our own sun. And yet, trillions of them course through your body each second without a trace. You never feel them. They leave no mark. To them, you and the Earth are as transparent as glass. It was in the mid-20th century that neutrinos were first confirmed to exist. They had been predicted by physicists to account for missing energy in radioactive decays, but catching one was a monumental challenge. Scientists built huge vats filled with clear fluid deep underground to shield them from other particles. In 1956, after years of trying, physicists detected neutrinos emitted from a nuclear reactor. A subtle flash of light in their detector signaled that a neutrino interaction had happened. It was a triumph. The ghost particle was real. With time, even larger and more sensitive neutrino observatories were constructed. One early detector in a gold mine in South Dakota used a tank of cleaning fluid. Another in Japan used 50,000 tons of ultra-pure water watched by thousands of light sensors. These detectors began to see neutrinos coming from the Sun, confirming our understanding that the Sun's core is powered by nuclear fusion that produces floods of neutrinos. They also caught neutrinos produced when cosmic rays strike the atmosphere. But neutrinos from more distant astrophysical events remained elusive for decades. Then, in 1987, something remarkable occurred in the Large Magellanic Cloud, a small galaxy near our own. A massive star reached the end of its life and exploded as a supernova. Hours before astronomers with optical telescopes saw the brilliant light of the supernova, underground detectors on Earth registered a flurry of neutrinos, about 24 of them, in a span of seconds. Those neutrinos had been released from the collapsing core of the dying star, and, unlike light, they escaped almost immediately, racing ahead of the supernova's visible blast. It was the first time humanity detected neutrinos from an extraterrestrial stellar explosion. They were heralds of the supernova, announcing it before the light arrived. This event marked the beginning of neutrino astronomy. We had directly observed an astrophysical phenomenon through these ghostly subatomic messengers. Today, neutrino astronomy has advanced further. One of the most ambitious projects is an observatory called IceCube, which is embedded in the clear ice near the South Pole. Sensors buried deep in Antarctic ice patiently watch for faint flashes caused by the rare interactions of neutrinos. In 2017, IceCube detected an extraordinarily high-energy neutrino, far more energetic than those from the Sun or typical supernovae. What made this event special is that scientists were able to trace the neutrino back to its source. They triangulated its incoming direction and pointed conventional telescopes that way. They found that the neutrino came from a distant galaxy with a blazing active nucleus, a quasar powered by a supermassive black hole. It appears that the colossal jets or winds from around that black hole had accelerated particles to extreme energies, producing neutrinos that sped across the universe to Earth. This was a monumental discovery. It identified a specific astrophysical engine, a galaxy with a ravenous black hole, as a source of cosmic neutrinos and probably high-energy cosmic rays as well. At long last, one of the ghost particles had carried to us the story of its birth, and we managed to understand it. Neutrinos are unique among cosmic messengers. Because they rarely interact, they can travel unimpeded straight out of places that light might not escape. The center of an exploding star, for instance, is so dense and hot that photons struggle and get trapped. But neutrinos fly out freely, bringing us news from the heart of the explosion. The regions around black holes are cloaked from view by gas and dust. But neutrinos born there can escape and tell us what's happening close to those abyssal objects. Each neutrino that we catch in our detectors is like a direct letter from some extreme corner of the cosmos, often from phenomena obscured to ordinary telescopes. From the gentle afterglow of creation to the invisible substance binding galaxies, from the yawning voids between the stars to sudden flashes of radio energy in the dark, from the subtle ripples of spacetime to the rain of ghostly particles, the universe has been whispering to us in a myriad of ways. Each of these whispers carries a piece of the cosmic story, a riddle waiting to be unraveled. The afterglow of the Big Bang tells of our fiery origins. Dark matter hints at vast, unknown realms of physics shaping what we see. Silent voids speak through their very emptiness, challenging us to understand the grand design of all things. Fast radio bursts are like urgent messages whose language we have yet to decode. Gravitational waves let us listen to the drumbeat of merging stars and holes in the fabric of reality. Cosmic rays and neutrinos deliver fragments of stars and collisions, flung across space to our doorstep. These are the celestial whispers, sometimes loud, sometimes nearly imperceptible, that remind us how much mystery still permeates the cosmos. As we listen to these many signals, we find ourselves connected more deeply with the universe. We learn that the dark stillness of the night sky is an illusion, for the cosmos is alive with subtle conversations. It speaks in light older than galaxies, in particles that journey for eons, in vibrations that stretch across space and time. We are newcomers in this ancient exchange, but we are learning the language of the stars bit by bit. Each discovery, each whisper heard and understood, brings us closer to comprehending the grand tale of existence. So we lie back beneath the sky, wrapped in the velvet darkness of a quiet night. The stars above seem to shine in silence. But now we know that silence is full of meaning. Overhead, the cosmic afterglow still gently hums its story of creation. Invisible matter holds us all in a vast gravitational hug. Unseen bursts flicker and fade at the edge of perception. Space itself occasionally rings with the memory of distant collisions, and an imperceptible mist of particles passes through us, a testament to events we have yet to fully fathom. The universe is not cold and mute. It is whispering, singing a lullaby in a language of eternity. In this calm and mysterious night, we take comfort that we are part of this cosmic drama. Our curiosity has opened our ears to the celestial whispers, and our hearts to the wonder they inspire. The more we listen, the more we learn that even the darkest corners of existence are filled with subtle light and sound. The stars, the void, and all that lies between are communicating, telling us their secrets across the vast gulf of space and time. And as we close our eyes in the twilight of our own understanding, we can feel the gentle chorus of the cosmos carrying us into dreams of infinite possibilities, soothed by the knowledge that the universe, in all its mystery, is softly speaking to those who care to listen. In the silent darkness, before time began its measured march, the universe was a seed of infinite potential. All that we know, every star, every grain of cosmic dust, every breath we take, was once condensed into a point smaller than a mote of dust. There was no light yet, no form or structure, just a hush of possibility, a void pregnant with creation. Then, in an instant so brief it almost defies meaning, that stillness was gently stirred. It was as though the cosmos drew a deep breath, a breath of creation, and began to expand. It started small and quiet. Space itself unfurled, doubling and redoubling in size with inconceivable speed. In that first tiny fraction of a second, the universe grew from microscopic to cosmic proportions. Yet it was a calm expansion, a silent swelling of space everywhere at once. No sound could echo in the vacuum. No resistance slowed this gentle push. As if guided by a delicate hand, the fabric of reality stretched smooth and flat. What had been infinitesimal now billowed outward, carrying with it the seeds of galaxies and stars yet to come. From within that first instant, had there been an observer, Impossible though it was, there would have been no dramatic explosion to witness. No sound could carry, and the brilliance of the event was everywhere at once, rather than a burst from a point. The newborn universe didn't explode outward. It expanded uniformly, so every place was like the center. An imaginary witness would have seen a hot, dense glow all around, growing rapidly fainter and cooler as space stretched. In that silent moment, creation was a soft flash of light and energy filling the void, an expansion more like a gentle rising tide than a violent blast. This primordial surge left an enduring imprint on the cosmos. As space stretched so swiftly, it became extraordinarily smooth and uniform. Any curvature or clumpiness that might have been was ironed out by the rapid expansion. The universe we inhabit was left almost perfectly even, with nearly the same conditions everywhere. In a way, it's as if a crumpled sheet of space was pulled taut in all directions, flattening out wrinkles and inconsistencies. By the end of inflation's momentary rush, the cosmos was remarkably flat and calm on the grandest scales, like a vast plain extending in every direction. In the wake of this expansion, the early cosmos appeared featureless to the casual glance. But hidden in that uniformity were tiny variations, the faintest of imprints. The inflationary push had magnified minuscule quantum fluctuations into subtle density differences scattered through the hot, dense, young universe. These were the merest speckles of overdensity and underdensity. Faint quantum murmurs stretched to enormous scales, like gentle whispers echoing across a great hall. Those delicate imprints would one day grow into the great cosmic structures we see now. In spots just a touch denser than their surroundings, gravity began to gather matter ever so slightly more. Over time, imperceptible clumps drew in more and more material, growing into galaxies and clusters of galaxies. Meanwhile, the furious growth of space eventually eased, and the mysterious energy that fueled it transformed. In a gentle transmutation, the driving force of inflation poured its energy into the creation of matter and light. What had been a state of pure expansion became a hot, glowing ocean of particles, a fog of newborn plasma filling the universe. For a long while, this newborn universe was an opaque glow, a brilliant fog of particles and light entwined. It was as if creation's afterglow was too dense and bright to let any light escape far. Only as the universe expanded and cooled over thousands of years did this fog begin to settle. Eventually, atoms formed, and the cosmos became transparent, allowing the first light to travel freely. That ancient light still surrounds us even now as a faint whisper, the cosmic microwave background, a gentle glow that is the echo of the universe's fiery infancy, smoothed and cooled by eons of expansion. The exact spark that ignited inflation remains one of the great cosmic mysteries. Some unseen field or energy, like a cosmic spring suddenly uncoiling, must have driven space to expand so feverishly. Why it turned on and off so quickly, and why at all, we do not yet know. But its effects we plainly see in the uniform heavens above, and perhaps, beyond the edges of our observable sky, inflation's effect did not end with our own universe. Some theories whisper that inflation might be eternal, still bubbling new universes into existence, even now. Our universe could be just one bubble among an endless, foamy sea of universes, each born with its own initial breath. If true, then what we call the Big Bang was just one tiny spark in a much larger cosmic fire, the breath of creation gentle as it was, may have echoed again and again, giving rise to a much greater multiverse beyond our cosmic shore. Beneath a limitless cosmic sky, the imagination drifts to mirror worlds that might lie beyond our own. If our universe was born from a cosmic seed, perhaps countless others sprouted alongside it, each forming their own reality. These are the dreams of the multiverse, a vision of infinite variety, where every possibility may unfold somewhere. In this grand collage of worlds, some universes could be almost familiar, with stars and galaxies like ours, while others might follow entirely different rules. Each would be a self-contained cosmos, yet we can't help but wonder if they sense each other in some faint way, like distant echoes or reflections catching glimpses of themselves in each other's light. Some scientists wonder if our universe is but one bubble among many, floating in an unseen expanse. In the multiverse idea, space beyond our view may be endlessly giving birth to new universes, each with its own laws of physics. Some bubbles might pop into existence with forces and particles, unlike anything we know. Others could resemble our universe closely, differing only in subtle details. Perhaps the arrangement of galaxies is slightly different, or the hues of stars are changed. The cosmos, then, would be not a single stage, but an endless ocean, sparkling with countless island universes, each a different answer to the cosmic riddle. One might picture this multiverse as an endless cosmic ocean of foam, with each bubble a universe unto itself. In this analogy, our universe is just one shining bubble floating in a vast, extra-dimensional sea. Occasionally, two bubbles might drift close and perhaps touch, causing ripples or merging briefly, while others remain solitary. From a transcendent vantage, one we can only imagine, you would see innumerable glowing bubbles spread out like a foam of worlds, each expanding, popping, or colliding. It's a whimsical image, but it helps us sense the grandeur of a multiverse, a boundless froth of realities where anything conceivable might happen in some distant bubble. In fact, another vision of the multiverse arises from the microscopic realm of quantum physics. Some physicists imagine that every time a quantum event has multiple possible outcomes, all outcomes occur, each in its own separate universe. According to this idea, reality continually branches into countless parallel worlds. In one such world, an electron spins one way. In another, it spins the opposite way. In one universe, a coin lands heads. In another, it lands tails. Even our choices might create splits. In one branch, life unfolds one way. In a different branch, it takes another path. These many worlds are like shadows of each other, ever multiplying. They would all be equally real, yet each unaware of the others, like parallel streams flowing side by side. In one imagined universe, the fundamental constants of nature, the strength of gravity, the charge of the electron, the speed of light, might have different values. In that cosmos, stars might form in unusual ways, or not at all. Perhaps galaxies cluster more tightly, or maybe no stable atoms can exist, so the universe is a diffuse fog. In another reality, physics could allow exotic phenomena we can't conceive, or have additional elements and forces. The multiverse invites us to imagine without limit. Worlds illuminated by twin suns, galaxies sculpted in unfamiliar shapes, and skies alive with colours beyond our spectrum. It is a cosmic library of all possibilities, an endless variety of existence. Perhaps there are universes where time itself flows in reverse, so that they begin in what we would consider an ending and move backward. In such a backwards world, Old stars might uncollapse into gas clouds, and shattered cups might leap back into wholeness. There could be realms where the very laws of cause and effect are strangely twisted, or where entirely new fundamental forces shape reality. Some universes might be almost entirely empty, quiet expanses with only thin wisps of matter, while others could be crowded with stars in a flamboyant display. With enough imagination, each universe in the multiverse becomes a story unto itself, some serene and harmonious, others wild and stormy. Together, they form a boundless collection of tales. For instance, amid this multitude, there might even be another universe much like our own. Perhaps somewhere, another Earth orbits another sun, a twin to our world, but with its own unique history. On that Earth, events might have taken a different turn. Civilizations rising and meeting different fates, cultures and languages unfamiliar to us. There could be people there, living out lives under alien constellations, maybe even wondering about other universes in the quiet of their nights. And there might be countless universes with no Earth at all, where something entirely different fills the niche of home for whatever beings inhabit those realities. The multiverse could contain every story we can imagine, and many beyond our imagining. Some thinkers have speculated that new universes might sprout in the most mysterious of places, inside black holes. When a massive star collapses under its own gravity, it falls into an infinitely dense point, a singularity, hidden behind a black hole's horizon. It's been proposed that such a collapse could rebound, not in our universe, but as a big bang in a separate, closed-off realm. In this view, every black hole might be a bridge to a newborn cosmos on the other side. Our own universe, then, might have germinated from the death of a star in another universe. And within our cosmos, each black hole could be carrying the seed of a new universe, a cycle of creation arising from collapse, like cosmic phoenixes born from ashes. These ideas are captivating, but for now, they remain speculative. We have searched the skies for any hint of other universes. Some scientists have looked for subtle patterns or cold spots in the cosmic microwave background, signs that another universe might have jostled ours in the distant past. Others ponder whether an inexplicable twist in the distribution of galaxies or an odd signal could betray a world beyond our own. So far, no clear evidence has appeared. If other universes exist, they remain hidden behind a veil we cannot pierce. The multiverse, as enticing as it is, lives in the realm of theory and imagination without confirmation. Yet the mere notion of a multiverse casts a spell of wonder on our minds. It reminds us that our own vast universe might be just one island in a boundless sea. When we gaze up at the starry sky, we are gazing at just a tiny fraction of existence. The idea humbles us, expanding our perspective of what everything could mean. We realize how much might lie beyond our sight and comprehension. We cannot visit these parallel worlds, nor even prove they are there. But thinking about them opens our minds to infinite possibilities. Under the quiet night, as we contemplate the multiverse, we feel both small and deeply connected to a grander existence. It is as if all those possible worlds, real or not, whisper to us that reality is far more vast and mysterious than we ever imagined. After drifting through the notion of countless unseen worlds, another profound question emerges gently from the silence. What is the nature of our own reality? If the cosmos might contain other realms, or if reality can branch into many forms, could it be that our universe is itself some kind of illusion or construct? Perhaps we are like characters in a story, believing our world is all there is, while beyond our experience lies a deeper truth. The idea takes hold quietly. Could we be living inside a cosmic dream, a simulation crafted by forces unseen? With that thought, we slip into another realm of wonder. Imagine our entire reality as a grand program running on some unfathomably advanced cosmic computer. Every atom, every star, every breeze, and every memory could be part of the code. To us, the stars and galaxies are vast, brilliant objects shining in space. But in this scenario, they might also be bits of data in a complex calculation. Like characters inside an intricate virtual world, we would play out our lives, seeing and feeling and striving, unaware of the underlying machinery. The laws of physics would be the rules of the program, consistent and unyielding, giving our world structure and order. Space would be the stage of the simulation, and time the ticking of its clock. To the characters inside a perfect simulation, the illusion would be complete. We see the sky's darkness sprinkled with galaxies and accept it as the natural cosmos. We feel the warmth of sunlight and the tug of gravity, never suspecting these might be programmed effects. Just as a dreamer accepts a vivid dream as reality until awakening, we take our experiences as the ultimate reality. Mountains, oceans, trees, our own bodies, all would be information given form. Perhaps every particle is like a pixel in a grand cosmic rendering, each following rules set by the code. And unless there were a glitch or a deliberate clue left for us, we'd have no reason to doubt the authenticity of our world. Ancient philosophers, long before computers, spoke of the world as illusory. In Hindu philosophy, the concept of Maya describes the world as a kind of cosmic dream or magic show, veiling a deeper reality. Today, some scientists and thinkers echo that idea in modern form, wondering if what we call reality might be a sophisticated simulation. Intriguingly, the language of nature is mathematics. The universe operates with elegant, precise laws, almost as if it follows a script. The orbits of planets, the branching of trees, the spirals of shells and galaxies, all can be described by equations, as though coded by a master programmer. And the constants of physics, those numbers that define the strengths of forces and the properties of particles, seem uncannily fine-tuned for complexity and life. If gravity were slightly stronger, or the charge of the electron slightly different, stars might not shine and atoms might not hold together. It's almost as if our universe hit a sweet spot that allows structure and consciousness to arise. Some ask whether that is pure chance or a sign of intentional design in a programmed cosmos. If our world is a simulation, who might be its architect? Perhaps an inconceivably advanced intelligence in another reality built our universe as an experiment, an art project, or even as entertainment. Some have speculated that our own far future descendants might run ancestor simulations, recreations of the universe and life in their past, to learn about history. In that case, we would be the unwitting inhabitants of a vast simulation, living out our lives in a meticulously modelled world. There could even be layers of reality, simulations within simulations, worlds nested like Russian dolls. Our civilization has already begun to create tiny virtual worlds in computers. One day, we might craft simulations so rich and detailed that the beings inside them are conscious and unaware of their artificial nature. If that happens, we would become creators of new realities, perhaps without the knowledge that our own reality is also created. It's a dizzying thought, a chain of universes, each giving rise to the next. Yet whether or not we live in such a cosmic dream, the experience of our lives remains genuine to us. The sunrise still paints the morning sky in gold and pink, and our joys and sorrows still feel real. If the universe is an artwork or a grand experiment, it doesn't diminish its beauty or our meaningful experiences. In fact, one might take comfort in the notion that there could be a purpose or audience for our existence, that in some higher level of reality, our stories are observed and perhaps even cherished. Simulated or not, we are part of this magnificent cosmos. We strive, we love, we learn, and we marvel at the stars. All of that is real to our minds and hearts. Life within a simulation is life all the same. The values we hold and the wonders we experience lose none of their significance. In a sense, being in a designed world could mean that love, creativity, and curiosity are part of the design, threads of meaning woven into the program. Naturally, we wonder, if this is a simulation, could we ever find proof from the inside? Perhaps a perfect simulation would leave no evidence of its artificial nature. It would be seamless. Still, physicists have pondered whether there might be subtle clues. Maybe at the smallest scales, space and time are not continuous, but made of tiny units, like the pixels of a screen, hinting at an underlying grid. So far, experiments have not revealed any such pixelation of space. It appears smoothed down to the tiniest lengths we can measure. Or perhaps the simulation has built-in limits, like a maximum energy or speed, beyond which physics behaves unexpectedly. We've looked for anomalous results in high-energy cosmic rays and particle collisions, but again, we've found no clear deviations. It could be that if we are in a simulation, it's been programmed with extraordinary fidelity to physical truth, making it effectively impossible for us to tell. And so we carry on, much as characters in a novel continue their story, unaware of the author, living sincerely and curiously, which is all we can do. Regardless of the ultimate nature of our universe, base reality, or some elaborate illusion, our quest to understand existence drives us onward. We peel back layer after layer of reality's mysteries, always seeking the fundamental truth beneath. That journey now leads us to examine the deepest threads of the cosmos. Perhaps by studying the tiniest bits of matter and energy, we will find a common origin for everything. We turn now to one such idea, a hopeful theory that beneath all particles and forces lies a single, unifying thread, tiny, vibrating strings weaving the fabric of reality. At the smallest scales of existence, far beyond atoms and the reach of any microscope, a curious possibility awaits. What if the fundamental particles we know, electrons, quarks, photons, and so on, are not tiny points at all, but little loops of energy vibrating like strings? In this imaginative framework, called string theory, each elementary particle is an unimaginably small, one-dimensional string oscillating at a frequency unique to that particle. Just as a violin string can produce different notes when plucked in different ways, a cosmic string could vibrate in different modes to produce different particles. An electron would be one note, a quark another, a photon yet another, all essentially the same kind of string, only vibrating differently. The universe, in this picture, is permeated with an ever-present music at scales billions of times smaller than an atom, an inaudible symphony of infinitesimal strings. String theory suggests a profound unity behind the kaleidoscope of particles and forces. Every particle we know, the electron, the proton, the photon of light, even gravity's graviton, would be fundamentally the same kind of object, a tiny string vibrating in its own way. The electron's string might hum a certain tune, giving rise to its mass and charge, while the photon's string plays a different tune that makes light. One particular vibration pattern corresponds to a graviton, the particle that carries gravity, meaning gravity slips naturally into this theory. In essence, all four fundamental forces and all forms of matter could be unified as various notes played on the same cosmic instrument. The countless types of particles and interactions in our world would then be like melodies emerging from one underlying string, each note precise, yet all related. In this elegant vision, the tapestry of reality is woven from tiny vibrating strands. If we could zoom into the fabric of the cosmos, far beyond the scale of subatomic particles, we might see these strings shimmering and looping through extra dimensions, connecting and combining in complex patterns. They would be the threads of existence, tying together things that seem separate. Perhaps the particle that makes up a distant star and a particle in your body are, at the deepest level, the same kind of string playing the same note in the grand symphony of nature. It's a beautiful idea that hints at an underlying harmony in nature, that at the heart of all diversity lies unity, a single fundamental form dancing in myriad ways to create the world we see. These fundamental strings, if they exist, are extraordinarily small, far smaller than anything we can currently observe. To get a sense of their scale, imagine enlarging an atom to the size of the solar system. A string on that scale might only be as large as a tree on Earth. Put another way, a string could be 100 billion times smaller than a proton. It's no wonder such strings, if real, elude detection. They are far beyond the reach of any microscope or particle collider we can build. We infer their possible existence through the mathematical consistency and elegance of the theory, not by direct sight. So far, no experiment has definitively shown that strings are real. They remain a compelling but hypothetical idea, a possible solution to many puzzles in physics that we have yet to confirm. Yet the allure of string theory is that it offers a potential theory of everything, a single framework in which all the forces of nature and all types of particle can be unified. It is as if the universe's countless moving parts could be traced back to one master design. To make this theory work, however, we must accept some strange implications. One of them is that our universe might have more dimensions than the ones we perceive. Only in a universe with additional hidden dimensions can these tiny strings vibrate in all the ways they need to produce the world we know. And so, our exploration of the very small leads us onward to consider dimensions beyond sight, the hidden rooms of reality that could be all around us. For a fanciful moment, imagine plucking one of these cosmic strings like a violin. Of course, they are far too tiny for any real instrument, but in theory, altering a string's vibration would transmute the particle it represents. It's as if the universe holds a hidden instrument, with every fundamental string sounding a note in the grand composition of reality. We cannot hear this music with our ears, but we can sense it in the harmony of physical laws. The notion that creation has a musical foundation is poetic, yet string theory makes it scientifically conceivable. A cosmos composed of melodies beyond our perception. We live our lives moving through three familiar dimensions of space, forward, backward, left-right, up-down, and one of time. This four-dimensional spacetime is the stage for all physics as we know it. But consider the possibility that the universe has more directions than the ones we see. Imagine discovering that your house has a secret room behind a wall, a space you never knew existed. In the same way, our universe might contain additional spatial dimensions, hidden from our senses, yet still there, shaping reality in ways we have only begun to suspect. It's hard to picture dimensions beyond our own, but analogy can help. Envision a world that's completely flat, like a drawing on a piece of paper. The beings in that flat world have length and width to move in, but no concept of height. Up and down are beyond their comprehension. If you, a three-dimensional being, reached into their 2D world, the flat creatures would only perceive the parts of you intersecting their plane. Suppose you dipped the tip of your finger through the paper. To those flat beings, a mysterious circle might appear, the cross-section of your fingertip. If you pushed your whole finger through, they'd see a circle that starts small, grows to a certain size, then shrinks and disappears as your finger went through. They'd have no idea that it was actually part of a 3D finger connected to a hand, existing in a dimension beyond their understanding. To them, the appearance and disappearance of that circle would be inexplicable magic. Similarly, if extra dimensions beyond our three exist, we might only catch perplexing glimpses of them when higher dimensional objects or effects intersect with our 3D world. One way extra dimensions might hide is by curling up into tiny, compact shapes that we don't notice. Think of a long, thin wire viewed from far away. It looks one-dimensional, like a simple line. But up close, you see it has a circular thickness. An ant could walk around it. Our space could be similar. It might have additional dimensions folded up at every point, rolled into tiny loops, so small that even an atom cannot traverse them. These are often called curled up or compactified dimensions. An electron might be free to move in the usual three large dimensions, but also subtly influenced by how it can move in the hidden small dimensions. The size of these hidden loops could be on the order of the Planck length, extremely tiny, which is why we haven't detected any hint of them directly. They're like secret corridors so narrow that only the tiniest vibrations, such as strings, can enter and feel their extent. In this scenario, the extra dimensions are all around us, but they're so minute that we effectively move right past them without noticing, much as a huge elephant might not notice the tiny grooves in the floor it walks on. Another possibility is that some extra dimensions are not tiny at all, but we are confined to a certain region or brane within a higher dimensional space. In this picture, our entire observable universe could be like a flat membrane floating in a larger dimensional arena. We and everything we see are stuck on this membrane, often called a three-brane, since it has three spatial dimensions. We can move within this brane but not off of it. Much like a bug confined to the surface of a leaf, can move around the leaf, but cannot jump to another nearby leaf. There could be other brane universes separated from ours by a gap in a higher dimension, other parallel sheets of reality, forever out of touch because we're each trapped on our own slice. Why wouldn't we see those other universes? Because all our usual particles and forces, except perhaps gravity, cling to our brain and cannot travel through the higher dimensional bulk. Gravity, being weaker and more universal, might leak off our brain slightly, which is one idea for why gravity is so comparatively feeble. It spreads out into unseen dimensions, diluting its effects. If this brain world scenario is true, the extra dimensions could be as large as, or even larger than those we know. But we'd never know directly because we're like shadow puppets moving on a wall, unaware of the room beyond it. For someone who could step into the unseen dimensions, feats impossible in our world would be effortless. A locked safe could be opened without a key by reaching through a direction we cannot access. One might walk around a wall through a fourth spatial dimension as easily as we walk around a corner in regular space. To us, such abilities would seem like magic, but they would simply be using the broader landscape of higher dimensions. These thought experiments stretch our imagination, reminding us how limited our perceptions might be, akin to flat creatures unable to conceive of up and down. If extra dimensions exist, our universe might be only a cross-section of a richer reality, and beings with access to those dimensions would experience a vastly expanded world. So far, if extra dimensions are real, they have kept themselves well hidden. Researchers have tried various experiments to find evidence of them. We have measured the force of gravity at very small distances to see if it deviates from the expected behavior, a potential sign that gravity is leaking into higher dimensions. We've also looked in high-energy particle collisions for anything that suddenly vanishes or shows up as missing energy, as that could indicate a particle slipping off our brain into an extra dimension. To date, all observations can be explained with 3 spatial dimensions and 1 time dimension. No obvious anomalies have demanded extra dimensions. But the absence of evidence isn't evidence of absence. The extra dimensions, if they exist, might be just beyond our current ability to detect, either because they're too small and subtle, or because we're confined in a way that's hard to overcome. Theoretical physicists keep the concept alive because it elegantly resolves certain puzzles, and because, in conjunction with string theory, it's a logical extension of our mathematics. Pondering these hidden dimensions expands our sense of what somewhere can mean. Just as the concept of other universes stretches our imagination outward, extra dimensions stretch it inward, adding new directions in the very fabric of reality. It teaches us humility. Our sensory experience might not encompass all that exists. Even as we find the idea challenging, it is also enticing. The universe might be like a book with additional pages or chapters that we have not yet been able to read. We are characters confined to one chapter, unaware of the fuller story. Yet, even without accessing these potential extra spaces, we still have plenty of mystery in the dimensions we can perceive. Space and time themselves, the 4-dimensional fabric we inhabit, hold profound secrets. Our journey continues back to those familiar dimensions, to examine how space-time bends and ripples, exploring the geometry of the cosmos and the echoes of infinity it may contain. Space and time form the flexible fabric of our universe, and gravity is the gentle sculptor of that fabric. Massive objects, like stars and planets, warp space-time around them, much as a heavy ball placed on a soft sheet causes the sheet to dimple. The moon orbits Earth, and Earth orbits the sun, not because they are tied by invisible strings, but because they roll along the curves that these massive bodies create in space-time. In daily life, we feel this as gravity, the Earth's mass bending space under our feet, holding us down. In the vastness of the cosmos, this same bending choreographs the motion of planets, stars, and galaxies. Every object with mass or energy tells space-time how to curve, and that curvature tells objects how to move. Gravity, in Einstein's description, is not a force that pulls magically at a distance. It is the shape of space and time, guiding objects as they drift along the contours that mass has laid down. Einstein also revealed that time is woven together with space, and it too is affected by gravity. A clock placed near a massive object will tick more slowly than a clock farther away in weaker gravity. Time itself runs a tiny bit slower at your feet than at your head when you stand, because your feet are slightly closer to Earth's mass. A minute effect, but real. Meanwhile, light, which has no mass, still feels the influence of curved space. If a beam of light passes by a massive star or galaxy, its path bends, like a runner curving around a steep valley. We observe this in the phenomenon of gravitational lensing. Distant galaxies and quasars, whose light is bent by the gravity of a closer cluster of galaxies in front of them. The result can be multiple images of the same distant object, or rings and arcs of light in the sky, where one galaxy's light has been smeared into a circle by another galaxy's curved spacetime. These are not mere tricks of glass, but distortions of space itself acting like a lens. Gravitational lensing is striking evidence that space can bend and warp, revealing the otherwise invisible shape of space-time through the funhouse mirror effects on light. This bending and curving of space-time leads us to ask about the overall shape of the universe. Just as the Earth's two-dimensional surface is curved into a sphere, our three-dimensional space could be curved in a higher dimension. If space-time has positive curvature, like a sphere, it might be that if you travel far enough in one direction, you'd eventually return to your starting point from the other side, even though you never turned around. Space would bring you full circle. If space-time has negative curvature, like a saddle shape, it would spread out infinitely and never loop back on itself, offering an endless, open expanse. And if space-time is flat, it would extend forever in all directions without wrapping around, like an infinite flat plane, or at least so vast that it appears flat to us in all observable portions. The best measurements we have of the cosmic microwave background's patterns and the distribution of galaxies indicate that the universe is very close to flat overall. If there is curvature, the radius of that curvature is much larger than the observable universe, meaning space feels effectively flat to us on the largest seen scales. Still, we cannot be entirely sure of the cosmic topology. Space might have a more complex shape. It could be finite, but without boundaries, like a higher dimensional analogue of a donut shape or other torus forms, or infinite and multi-connected in ways our observations haven't yet noticed. The question of whether the universe is finite or infinite, and how it might wrap around, remains one of those tantalizing open questions. It's one of the echoes of infinity in cosmology. Either space truly goes on forever, or it loops in on itself in a way that if we journeyed long enough, we might eventually traverse the cosmos and come back to where we began. For example, if space is curved like a sphere, a spacecraft flying straight ahead long enough could eventually end up back where it started, arriving from behind without ever turning around. It would be akin to an airplane on Earth, flying continually east and eventually coming in from the west. The travellers might never sense the curvature of their path in local space, but after an immense journey, they'd discover they had looped around the cosmos. On the other hand, if space is flat or saddle-shaped, that looping would never happen. One could travel an infinite distance and always see new galaxies ahead. Our universe seems so vast that for now, we see no sign of light wrapping around, no repeated patterns that would hint we've been here before. If space does close on itself, it does so on scales far larger than what we can observe. So we lean toward the view of an effectively infinite, or at least unbounded, cosmos. Space-time not only curves, it can also ripple and ring. When massive objects accelerate or collide, they create disturbances in space-time that spread outwards at the speed of light. These are gravitational waves, ripples in the very fabric of space and time. Imagine two black holes spiraling in toward each other. As they twirl faster and closer, space-time around them quivers, and waves emanate outward like the concentric ripples on a pond after a stone is dropped. After traveling for billions of years, these waves wash over Earth, stretching and squeezing distances by a tiny amount as they pass. They are incredibly faint. By the time they reach us, the effect might change the length of a 4-kilometer measuring arm by less than the width of an atom. Yet with exquisitely sensitive instruments, humanity has begun to detect them. We have essentially built giant ears to press against the cosmic fabric, listening for the subtle symphony of space-time. The first detection of gravitational waves was like hearing the quiet chirp of the cosmos after eons of silence. Our instruments recorded a fleeting strain, the final moments of 2 black holes merging in a galaxy far away, a sound not of pressure in air, but of oscillations in existence itself. Since then, we have heard multiple such events: the collision of neutron stars, dense remnants of supernovae, sending vibrations that not only shook space-time, but created heavy elements and lit up the sky with gamma rays. More black hole mergers, each with its own mass and spin, each ringing space-time in a unique way. These waves carry information that no light can. They come from events shrouded from view, like black hole mergers, which emit no light, and from distances so great that the signals are incredibly weak by the time they reach us. Yet they arrive, whispering their stories. Each gravitational wave detection is a direct message in the language of gravity, telling us of titanic events across the universe. These waves remind us that space-time is not a static, empty stage, but a dynamic medium that can stretch, squeeze, and resonate. When a gravitational wave passes through, for a brief moment, everything in its path, you, me, the Earth itself, is gently stretched in one direction and compressed in the perpendicular direction, then vice versa as the wave oscillates. We don't feel it at all at the human scale, but sensitive laser interferometers sense that tiny change. It's as if the universe has a memory of every cataclysm, and those memories travel indefinitely as distortions in space-time. By hearing these echoes, we connect with events that happened long ago and far away. It is a profound new way to observe the cosmos, as if we had been deaf and suddenly gained hearing. In the stillness of the night, one can imagine the universe filled with these quiet songs, the ongoing chorus of creation and destruction, the gentle ringing of space-time from distant events, a cosmic lullaby in the dark. And now, from the grand ballet of curved space-time, we gently turn to the tiniest scale of all. We have seen how, on the largest scales, the universe displays a majestic order. Galaxies follow the curves of space-time, and space-time in turn responds to mass and energy. To explore further mysteries, we must journey into the opposite extreme, the realm of the very small. Let's imagine we could shrink ourselves millions of times over, diving into a grain of sand, descending past the scale of cells and molecules. As we become as small as an atom, a strange new world opens up. At first, the atom might look like a vast arena, a tiny bright nucleus at the center, and electrons as diffuse clouds surrounding it at a great distance. If we shrink further, down near the nucleus or riding on an electron, we would enter a realm where the usual rules of nature change dramatically. We are drifting into the quantum world, where particles and waves intertwine and certainty dissolves into probability. Deep within the atom, reality obeys rules that defy our everyday intuition. The solid, reliable world we perceive gives way to a flickering quantum haze. Particles in this realm don't act like little billiard balls following neat paths. They behave more like spread-out waves of possibility. An electron bound to an atom doesn't orbit the nucleus like a planet around the sun. Instead, it exists as a cloud of potential, a smeared presence, occupying many places at once around the nucleus. We call this region an electron cloud, or orbital. It's the zone where the electron might be found if we look. But until we measure it, the electron doesn't have a single location. It's as if the electron is a mist, enshrouding the nucleus in a fuzzy sphere. Only when we interact with it, when the atom emits a light particle, or when we probe the electron's position, does the electron appear to collapse to a definite spot. In the absence of observation, the electron is more truthfully described by a wave function, which encodes a range of possibilities. This is a radically different picture of matter, not a point circling, but a haze of existence. If we could peer inside that atom during its quiet moments, we would find that most of it is astonishingly empty space. The nucleus at the center is incredibly small and dense, containing more than 99.9% of the atom's mass, in a volume just a tiny fraction of the whole. The electrons hover far out, relatively speaking, leaving the intervening space mostly void. To get a sense of the scale, if an atom were the size of a large cathedral, the nucleus might be a grain of sand on the altar, and the electrons would be like motes of dust buzzing around near the ceiling. The space between nucleus and electrons is empty in the sense of matter, but it's filled by the electric field that keeps the electrons bound to the nucleus. When you press your hand against a tabletop, what stops your atoms from passing straight through the table's atoms is the electromagnetic repulsion between the electron clouds in your hand and those in the table. No two atoms actually touch in a classical sense. Their electrons simply push against each other's fields. Thus, what feels solid is actually the force fields of countless electrons resisting overlap. We live in a world where matter is mostly emptiness, given form and hardness by the invisible fields and the perpetual dance of tiny particles. The quantum world allows an entity to be in a combination of states until we observe it. This principle is known as superposition. An electron can spin clockwise and counterclockwise, in a certain sense, at the same time, or take multiple paths simultaneously through an apparatus. A striking demonstration is the famous double-slit experiment. If we fire a single electron at a barrier with two narrow slits, the electron behaves not like a single pellet passing through one slit or the other, but like a wave that passes through both slits at once and interferes with itself on the other side. We see a pattern of light and dark bands on a screen, an interference pattern, even though we sent electrons one by one. Each electron seems to explore all options, going left, going right, as a spread-out wave, and only when it hits the screen, or we otherwise measure it, do we get a single dot, a single outcome. If we try to peek and find out which slit the electron actually went through, the illusion collapses. The electron picks a path, and the interference pattern disappears. It's as if nature, when not under interrogation, is content to let possibilities blend and overlap. But when we demand a concrete answer, nature gives us a single result. This isn't because our measurement forced the electron one way or another in a physical pushing sense. It's just how reality behaves at that scale. Until interaction, the electron genuinely is in a limbo of both paths at once, here and there simultaneously. It defies common sense, yet it's a fundamental aspect of how our universe works. Even what we usually think of as empty space isn't truly empty. The quantum vacuum is a seething background of energy and potential. According to quantum theory, fields permeate all of space, like the electromagnetic field, the electron field, etc., and even in their lowest energy state, they aren't perfectly still. Instead, they undergo tiny fluctuations. Pairs of particles and antiparticles can briefly flicker into existence from the vacuum, borrowing energy from the void, and then vanishing an instant later, and returning that energy. These are called vacuum fluctuations, or virtual particles. They're not something we can observe directly. If you try to catch them, the act of observing gives them the energy to become real, or otherwise they annihilate and disappear. But we can see indirect effects. For example, these vacuum fluctuations cause a slight force between metal plates in a vacuum, the Casimir effect, and contribute small corrections to the energy levels of atoms. In essence, the emptiness of space has a baseline restless energy, as if even in perfect quiet, there's a soft background hum. This quantum foam is like the universe's subtle breath, an ever-present, low-level whisper of creation and annihilation happening just beneath the veil of the classical world. Among the most mysterious phenomena in quantum mechanics is entanglement, a deep connection that can form between particles. When two particles become entangled, they share a single quantum state, even if they fly far apart from one another. It's as though they become two parts of one system. If we then measure one of the entangled particles, the other particle responds instantly, no matter the distance between them. For example, two electrons might be entangled such that their spins are opposite. If one electron is measured and found to have spin up, the other will be found spin down, even if the two electrons are on opposite sides of the galaxy. This correlation happens with no exchange of signals as far as we can tell. It simply is. Einstein famously described entanglement as spooky action at a distance, because it seems to violate our sense that objects need a mediating influence to affect each other. But entanglement doesn't allow us to send information faster than light, so it doesn't actually break relativity. It's more like two perfectly coordinated random number generators that always output opposite numbers once checked, without any communication. Entanglement suggests that on a fundamental level, the notion of separateness might be an illusion. Particles that were once together and entangled remain in some sense a single system, a single thing, even when apart. It's as if the universe can tie two distant particles in a secret knot, so that what happens to one immediately influences the other's state. This phenomenon has been repeatedly confirmed in laboratories and even used in emerging technologies like quantum cryptography and the early stages of quantum computing. It invites a philosophical wonder. Perhaps everything in the universe was entangled at the very beginning, the aftermath of the Big Bang, connecting all things in ways we don't fully understand. The quantum domain often seems random or capricious. An atom's nucleus might decay at one moment or another, and we cannot predict exactly when, only the probability. A particle's position is not fixed until measured. To our minds, raised on cause and effect, this inherent uncertainty can feel unsettling. And yet, it is this very uncertainty that gives rise to stable structures and the rich world of possibilities. Quantum uncertainty prevents atoms from collapsing. If electrons had exact positions and momenta, they could spiral into the nucleus. The uncertainty principle keeps them spread out, and it allows stars to shine via quantum tunneling in nuclear fusion. Moreover, when you have enormous numbers of particles together, the wild individual behaviors average out. That's why a baseball or a planet moves in a way we can calculate precisely using classical physics, even though each particle within them follows quantum rules. The collective behavior of zillions of particles yields the solid, predictable world we navigate daily. Thus, the classical world emerges from the quantum world when viewed in bulk. The sharpness of a measuring stick, the reliability of a clock, the solidity of a rock. All these macroscopic certainties are born from the averaging of microscopic uncertainties. This reconciliation between quantum and classical is subtle and deeply reassuring. It tells us that the strange quantum haze underlies everything, but when scaled up, it creates the dependable reality we know and trust. The border between the quantum and classical is not a brick wall, but a gentle gradient, where probabilities smooth out into near certainties. To better understand the quantum foundation of everything, physicists have found it useful to think in terms of fields. Instead of imagining little particles pinging around, we imagine that for each type of particle, there is a field filling all of space, like an invisible grid or ocean. A particle is then a localized excitation, a little wave or vibration in its respective field. For example, there is an electron field everywhere, and an electron is what we call a bundle of energy in that electron field. There's an electromagnetic field everywhere, and a photon, a particle of light, is a wave packet traveling in that electromagnetic field. In this way of thinking, empty space isn't empty. It's the baseline state of numerous fields stacked on top of each other. What we perceive as particles interacting, say, an electron repelling another electron, can be viewed as the electron fields interacting through the electromagnetic field. This picture emphasizes how deeply interconnected everything is. The light from a distant star is not a thing that traveled million years through empty void. It is a disturbance in a field that extends from that star to here, binding the two locations with an unbroken line of presence. When a star shines, it excites the electromagnetic field in its vicinity, and that excitation spreads outward, and when our eyes or telescopes absorb that light, the same field is vibrating here. In a real sense, the star and the observer share the same field, are part of the same physical entity, spread across space. Thinking in fields removes the hard boundaries between objects. All matter and energy become ripples on a cosmic pond. When you touch a chair, the electrons in your hand and in the chair are ripples in their respective fields, and the electromagnetic field mediating between them ensures they never actually meld. You and the chair are connected by fields. In fact, at the field level, you're part of one enormous system. This is a very holistic viewpoint. Instead of a universe made of separate billiard balls bouncing around, it's a universe of overlapping waves, where separateness is an effective idea at large scales, but fundamentally, everything is woven into one vast, complex tapestry of energy. And so, as we marvel at these tiny dancers on the stage of the unseen, we find they echo the grand patterns of the cosmos, from the inflationary breath that launched the galaxies to the quantum fluctuations that dance in every empty corner. The universe shows us mystery and wonder at every scale. The very large and the very small sing verses of the same cosmic song, harmonies we are only beginning to understand. We float here at the intersection of the immense and the minute, humbled by the interconnectedness of things and by how much remains unknown. In the gentle darkness of this moment, we let these insights wash over us without needing every answer. We have travelled from the birth of time to the subatomic heart of matter, and still the cosmic riddles abound. In the silence that follows, we understand this is not an end, but a resting point in a much longer journey. The story of the universe stretches far beyond the horizon of our knowledge, its mysteries continuing to whisper in the dark. For now, we let the soft cosmic lullaby guide us into rest, comforted by the knowledge that the journey carries on, ever onward among the stars. In the stillness of a clear night long ago, our ancestors gathered under a sky brimming with stars. Without any city lights to dim it, the Milky Way arched overhead like a pale river of light. Gazing upward, those early people did what humans do best. They imagined. They connected the sparkling points into shapes of heroes, beasts, and gods, weaving stories into the very fabric of the night. Every cluster of stars became a canvas for the human imagination. Every constellation a tale written in starlight, whispered from one generation to the next. They saw a mighty figure striding across the heavens, a bright belt of 3 stars gleaming at his waist. The ancient Greeks called him Orion, the great hunter of myth. High in the summer sky, a scorpion with a curved tail crawled among the stars. Scorpius, the creature that, in Greek lore, felled the boastful Orion. The gods placed them on opposite sides of the sky, it was said, so that the hunter and the scorpion would never meet again. Indeed, when Scorpius rises, Orion slips below the horizon, an eternal celestial chase played out each year. Not far from Orion's belt, a tiny cluster of stars glimmers like a pinch of diamond dust. To the Greeks, these were the Pleiades, the 7 sisters, transformed into stars to escape Orion's pursuit. That hazy little cluster has inspired myths in many cultures. In one Greek tale, the sisters shine as a reminder of protection and sisterhood. High in the Andes, the rising of those stars signaled the time to plant crops, a promise of abundance from the sky. Across the world, people looked up at the Pleiades and saw 7 siblings, 7 maidens, 7 divine beings, their delicate light holding immense meaning for those watching from below. Different peoples, gazing at the same stars, often saw surprisingly similar visions. Where one culture traced a hunter, another saw a guardian spirit or a beloved animal. The pattern we know as the Big Dipper, part of Ursa Major, was seen by many Native American tribes as a great bear. In one Iroquois legend, the bowl of the Big Dipper is the bear, and the 3 stars of the handle are hunters forever chasing it across the sky. Far across the world in China, those same 7 stars were known as the Northern Dipper, envisioned as a celestial ladle or chariot of the heavens, associated with the balance of fate. Each culture filled the night with its own stories and symbols, yet all shared the impulse to humanize the sky, to find familiar shapes in the darkness and tell tales about them. Even the soft band of the Milky Way became a story written in the stars. The Greeks saw it as a stream of milk from the goddess Hera, spilled across the heavens. In China, it was a silvery river separating 2 lovers, the Weaver Girl star, Vega, and the cowherd star, Altair, who are allowed to meet just once a year when a bridge of birds forms across the sky. On that night, celebrated in festivals even now, the magpies unite to let love cross the Milky Way. Such tender myths gave the immense, impersonal night a warm, human touch, turning distant lights into symbols of devotion and longing. Under this dome of stars, our ancestors found guidance as well as inspiration. The patterns in the sky served as a calendar and compass. The appearance of certain constellations heralded seasonal changes, telling farmers when to sow and when to harvest. To the ancient Egyptians, the yearly rising of Sirius, the dog star, just before dawn, foreshadowed the flooding of the Nile, and thus the renewal of their lands. In the Pacific, Polynesian navigators steered by the stars. They knew the night sky's map by heart, using the rising and setting of specific stars as a lattice of pathways across open ocean. What began as stories and dreams also became practical knowledge. The sky was not only a storybook, but also a reliable clock and guide for those who learned its patterns. Around campfires and hearths, elders pointed to the heavens and passed down these starry tales. Imagine the comfort those stories offered on a long night. The notion that above the dark forests and wide seas, there were familiar friends shining down. A lost traveller could find north by the steady glow of Polaris, the North Star, and a lonely child could look up and find heroes and animals watching over them from the sky. By naming and personifying the stars, people gentled the vast unknown, turning an indifferent expanse into a richly populated wonderland that felt almost like home. Every culture under one sky was engaged in the same act of creation, finding order and meaning in the glittering chaos above. Whether it was an Egyptian goddess arching over the earth, her body aglow with stars, or the Navajo figure of a slender holy man outlined in the pattern of Orion, the heavens became a grand tapestry on which we embroidered our values, fears, and dreams. In those constellations, ancient peoples saw reflections of their own lives, eternal romances and tragic mistakes, great hunts and great heroics, cautionary tales and hopeful prophecies, all suspended in the night for eternity. The sky was a mirror for the human soul, and as long as the stars moved in their predictable dances, those stories could be retold to guide and inspire. Night after night, generation after generation, these myths written in starlight-bound communities together, sitting under the same sky, telling the same tales, our ancestors found continuity and connection. The stars became an eternal storytelling circle. A hero's bright star assured a tribe that courage and honor would be remembered. A pair of lovers cast among the stars reminded everyone that love endures beyond separation. A wicked figure punished in the sky served as a lasting lesson across centuries. In the hush beneath the cosmos, when crickets chirped and the firelight flickered, the night was alive with these luminous characters and their never-ending dramas. Such stories made meaning out of the sparkling scatter of lights. Random stars were linked into patterns and imbued with moral and spiritual significance. Through imagination, humanity transformed a cold, indifferent night into a familiar stage for timeless narratives. When something unexpected streaked across the sky, a comet with a glowing tail or a sudden new star, new myths arose to explain it. A comet might become a celestial dragon or a harbinger of change. A supernova could be interpreted as the bursting forth of a new deity or the portent of a great event. In this way, the cosmos spoke through myth. And in listening to these myths, people found not only entertainment, but comfort and wisdom. The vast unknown was made knowable through story. Yet even as these constellation dreams nurtured the human spirit, they planted seeds of a different kind of curiosity. People began to wonder about the stars in a new way, not just who they were in myth, but what they were in reality. What were these lights, truly? How far away were they, and why did they move as they did? The myths, as beautiful as they were, could not fully satisfy an emerging thirst to know. In time, the desire to understand grew alongside the desire to imagine. The sky that had been a canvas for legends became as well a source of puzzles to be solved, patterns to be mapped, truths to be uncovered. So, under those same stars, the first astronomers were born. While the old stories still hung in the air, a new kind of observer began to watch the heavens with a more careful eye. These early sky watchers started to measure and record what they saw, seeking an underlying order in the movements of celestial lights. In the embers of myth, a spark of science was glowing. Gently, almost imperceptibly, humanity's relationship with the stars was beginning to shift from one of pure reverence and storytelling to one that also included careful observation and wonder of a different kind. In the quiet hours before dawn, in ancient Mesopotamia, an Assyrian priest astronomer stands atop a mud-brick ziggurat, peering at the last stars of night. He holds a clay tablet etched with numbers, records of the previous night's sky. In that cradle of civilization, long before modern science, such priestly sky watchers began a remarkable tradition. They systematically recorded the movements of the heavens. Night after night, year after year, they noted how the wanderers, the planets, moved against the backdrop of fixed stars, how the moon cycled from thin crescent to full orb and back, how certain stars rose just before sunrise at particular times of year. These were the first astronomers, though they did not use that word, and to them charting the sky was both a sacred duty and a practical craft. With each observation, patterns emerged. The early stargazers of Babylon discovered that the heavens ran with regularity, almost like clockwork. By counting the days between the moon's phases, or tracking the repeating path of Venus in the morning and evening sky, they learned to predict celestial events. They divided the sky into sections, creating some of the constellations and zodiac signs we still use today as reference points. They devised a way to measure angles and time based on the number 60, a sexagesimal system that gave us 360 degrees in a circle and 60 minutes in an hour. Those convenient units we still use for geometry and timekeeping are a direct legacy of ancient sky watchers dividing up the dome of stars. What began as mythic storytelling evolved into meticulous documentation. The stars were still seen as meaningful, but now the meaning came not only from mythic characters, but from the numbers and cycles themselves. Astronomy became the foundation of calendars that guided entire civilizations. The priests of Egypt, for instance, watched the eastern horizon for the yearly first appearance of Sirius, the brightest star. Its rising in pre-dawn summer foretold the flooding of the Nile, knowledge vital for agriculture. By knowing when that star would return each year, they could plan plantings and rituals around the life-bringing floods. In Stonehenge's Great Stone Circle in England, and at sites built by the Maya in Central America, and the Inca in the Andes, we see alignments with the solstices and equinoxes. Huge stones and temples were positioned so that on the longest day of summer, or the shortest day of winter, the sun's light would pierce a special corridor or window. These ancient observatories, carved in rock and earth, are silent testaments that tracking the heavens was a universal human endeavour. Long before mechanical clocks or modern instruments, people built monuments to mark the turning of the year by the sun and stars. It wasn't only the cycles of time that intrigued these early astronomers. It was also the measure of the cosmos itself. In ancient Greece, thinkers brought a new level of inquiry. They sought not just to record the heavens, but to explain them in rational terms. Around 250 BCE, Eratosthenes of Cyrene, working in Egypt, famously measured the size of the earth with remarkable accuracy. Using nothing more than a stick's shadow in one city and a deep well in another, he deduced that the Earth's surface is curved and calculated its circumference to within a few % of the value we know today. Humans, for the first time we know of, had measured their planet. By observing the angle of the sun's rays at two different locations at the same moment, Eratosthenes used simple geometry to estimate Earth's size, a breathtaking insight for its time, showing that careful observation and reasoning could reveal the scale of the world. Greek astronomers and philosophers pushed further. They catalogued hundreds of stars and noted their positions and brightnesses. Hipparchus, one of the great ancient astronomers, created the first star maps and even discovered that the stars' positions slowly shift over centuries, the precession of Earth's axis. Others, like the mathematician Ptolemy in the 2nd century CE, worked out elaborate models to explain the wandering of the planets. In Ptolemy's geocentric model, the Earth sat at the center of everything, while the Sun, Moon, and planets moved in complex loops, epicycles, around us. This model was complicated, but it could predict the motions of the planets fairly well, and endured as the accepted cosmic scheme for over 1,000 years. It was an age when observation mixed with philosophy and some guesswork. They got much right, like the spherical Earth and the idea of mapping the sky, and some wrong, like Earth being the universe's center. But they demonstrated the power of systematic observation and mathematics to understand the heavens. Not everyone in antiquity was convinced that Earth lay at the center. Now and then, bold ideas were proposed. The Greek thinker Aristarchus, as early as the 3rd century BCE, suggested that the Sun, not Earth, was at the center, with Earth and the other known planets orbiting it. This heliocentric idea was far ahead of its time and was largely dismissed by his contemporaries in favor of the Earth-centered view. Still, the seed of that idea survived in obscure texts, lying dormant for many centuries, awaiting rediscovery. Meanwhile, beyond the Mediterranean world, astronomy flourished in other cultures too. In ancient China, imperial astronomers kept detailed records of eclipses, comets, and guest stars that suddenly appeared in the sky. One such record from 1054 CE notes a new star so bright it was visible in daylight for weeks. We now know this was a supernova, the explosion that created the beautiful Crab Nebula. Chinese skywatchers, working for the emperor, treated the heavens with utmost seriousness. An eclipse could be seen as an omen, and there are tales of astronomers in earlier times who were punished for failing to predict one. In India, scholars calculated planetary motions and developed sophisticated calendars. In the Islamic Golden Age, medieval astronomers built upon Greek and Indian knowledge. They gave many stars the Arabic names we still use, like Altair, Betelgeuse, and Vega, perfected astronomical instruments, and preserved classical learning during Europe's Dark Ages. Across the ocean, the Maya had observatories like El Caracol, and created calendars of stunning accuracy, timing Venus's appearances and predicting eclipses. All around the world, across different eras, the human gaze fixated on the sky followed a common thread: observe, record, predict, and seek to understand. For all their cultural differences, those early astronomers shared a belief that understanding the sky could offer practical benefits and perhaps even glimpse the will of the heavens. Sometimes their knowledge meant the difference between chaos and order. A famous story from Greece tells how Thales of Miletus predicted a solar eclipse in 585 BCE. When the eclipse occurred and day turned to night on cue, 2 warring armies were so astonished that they laid down their arms and declared a truce. We cannot be sure if Thales truly predicted it or was just lucky, but the tale illustrates the esteem and awe afforded to those who could glean order from the sky's seeming caprice. In China, as mentioned, an ancient legend speaks of 2 court astronomers, Shi and Ho, who failed to predict an eclipse and were said to have been executed for their negligence. A perhaps embellished story, but one that underscores how seriously rulers took the task of tracking the heavens. Over time, the accumulation of observations and the cross-pollination of ideas from different cultures brought humanity to the brink of a profound transformation in understanding. By the late Middle Ages and the dawn of the Renaissance in Europe, cracks were forming in the old Earth-centered cosmic model. The delicate hints first whispered by Aristarchus long ago were about to be heard again, louder this time. In 1543, Nicholas Copernicus published his heliocentric theory, reviving the idea that Earth is just another planet orbiting the Sun. This was a daring reimagining of the cosmos that challenged a worldview held for millennia. Many resisted it, but the idea had taken root. A few decades later, Galileo Galilei turned the newly invented telescope to the sky, and the universe suddenly revealed new secrets. Galileo saw 4 moons orbiting Jupiter, proof that not everything revolved around Earth. He observed the phases of Venus, which made sense only if Venus circled the Sun. Piece by piece, evidence accumulated that the old Ptolemaic model was wrong. The sun-centric vision of Copernicus was correct, and our Earth had been dethroned from the cosmic center. Imagine the wonder and disorientation that people must have felt. For countless generations, humans assumed the cosmos was built with us at the middle, that the celestial dance was choreographed around Earth. Now, in what has been called the Copernican revolution, our world was revealed to be one of several planets, and not particularly central at all, just a small globe whirling in the vastness. It was a humbling and exhilarating shift in perspective, perhaps the greatest shake-up in our understanding of the universe ever. Earth became, in the collective human imagination, a lonely voyager in an unfathomably large sea of space. As this new reality sank in, it brought both excitement and a kind of existential loneliness. If Earth was not the focus of creation, if it was merely one island among innumerable others, then new questions arose that earlier generations hadn't fully articulated. What other islands are out there? Could they be homes to other beings, other lives, perhaps other minds that gaze at the stars as we do? When Earth was unique and central, such questions felt abstract. Now they felt inevitable. With the revelation that planets are commonplace, the ancient speculation about worlds beyond our own took on new urgency. Our ancestors had peopled the sky with gods and monsters. Now we began to wonder if it might be populated with fellow observers. The stage was set for a new chapter in our cosmic story. Humanity, armed with telescopes and a bold new perspective, turned its gaze and its curiosity outward, from the comfort of our familiar sun and moon to the deep cosmos beyond, asking one of the most profound questions we can ask. Are we alone in this immense expanse? At last, we understood that our Earth is not the center of all things, but just one world adrift in a vast cosmic ocean. From space, we've seen our planet as a tiny, fragile ball of blue and white, a pale blue dot suspended in darkness. Astronauts who have looked back at Earth from orbit often describe a deep sense of solitude mixed with wonder at that sight. Our entire world, with everyone we know and love, hanging together in the void. It is a beautiful loneliness. Earth appears as a solitary oasis wrapped in gauzy clouds, with no obvious companions nearby in the endless night. In that profound isolation lies one of the greatest riddles we face. In all the expanse of the universe, are we truly alone? For a long time, the question was academic, even fanciful. Many people simply assumed the stars were distant suns with their own worlds and perhaps their own creatures. But it was only speculation. In the early 20th century, Some astronomers thought they saw evidence of life next door on Mars, linear markings that were misinterpreted as canals built by intelligent Martians. Venus, eternally cloaked in clouds, was imagined by others to be a lush jungle world teeming with strange life. These ideas filtered into popular culture. Stories of Martian invaders or Venusian civilizations became common in fiction. But when we actually sent spacecraft to our neighboring planets, reality proved less kind to our hopes. The canals on Mars turned out to be an optical illusion. There were no alien-built waterways, just barren craters and deserts. Mars was cold, dry, and seemingly lifeless on the surface. Venus, when probed by our sensors, revealed itself not as a tropical paradise, but as a hellscape. Its thick clouds hid a surface hot enough to melt lead, with crushing pressure and poisonous air. The romantic notions of life on nearby worlds evaporated under the harsh light of data. One by one, our sibling planets in the solar system seemed to say, no, life did not take root here. By the late 20th century, it became clear that in our solar neighborhood, Earth is the only known cradle of life. The moon is airless and sterile. Mercury is seared by the sun. Jupiter and the gas giants, though fascinating, are composed of turbulent gas, unlikely to host life as we know it. Their moons offered some hope, and indeed, we now suspect a few might have subsurface oceans and perhaps microbial life. But no evidence of alien civilizations next door greeted us. This realization, that life might be exceedingly rare, even in a system full of planets, was sobering. The more we learned about our solar system, the lonelier our home planet seemed. And so, we turned our gaze and our instruments outward, beyond the solar system, and we began to listen. If neighbors in our own system were mute, perhaps voices from the stars would speak. In 1960, astronomer Frank Drake aimed a radio telescope at two nearby sun-like stars in the first modern search for extraterrestrial signals. He heard only silence, but the endeavor marked the beginning of SETI, the search for extraterrestrial intelligence, which continues to this day. Over the decades, as technology improved, we built vast radio dishes and arrayed antennas to scan the sky for any hint of an artificial radio transmission. We listened at frequencies we thought an intelligent species might use to hail others or leak their communications. So far, every sweep of the dial has yielded nothing definitive, just the natural hum and crackle of stars and galaxies. At times, there have been tantalizing blips. Most famously, the WOW signal detected in 1977, a strong, unexplained burst of radio waves that lasted only a minute and was never heard again. It remains a curiosity, possibly a technical glitch or an odd natural emission, but no confirmed hello from ET has ever been received. This eerie silence leads us to Fermi's famous question, posed over lunch one day in 1950. Where is everybody? If the cosmos is filled with stars and planets, and presumably many of them older and more advanced than ours, why haven't we seen any sign of alien civilizations? This conundrum, known as the Fermi paradox, has no easy answer. It could be that life, especially intelligent life, is far more rare than our optimism assumed. Or it could be that technological civilizations are common, but short-lived, snuffed out by cosmic disasters or their own mistakes before they can reach out very far. Perhaps they're out there, but keeping quiet. Or maybe we're not listening the right way. The paradox hangs in the quiet night like an unanswered echo. In a galaxy of hundreds of billions of stars, our telescopes and antennas find no chatter, no obvious beacons, only our own questions beaming out into the dark. Still, the vastness of the universe counsels patience and humility. Our search has only skimmed a tiny fraction of the sky, and our listening time has been short on cosmic scales. There are as many stars in the observable universe as there are grains of sand on all Earth's beaches, maybe more. Around many of those stars, we now know, there are planets, countless worlds orbiting suns big and small. Even if life is rare, the sheer number of opportunities might mean it has arisen many times. It's like standing on a shore and looking at an ocean that stretches beyond the horizon. You wouldn't conclude fish don't exist just because you don't see any on the tiny patch of beach you're standing on. The universe's enormity both troubles and reassures us. It troubles us because distances between stars are immense, making communication difficult and travel, with our current technology, practically impossible. Any neighbours might simply be too far for a shout or a voyage. It reassures us because it suggests hope. If the dice of life were rolled on so many planets, perhaps some came up alive, and some of those evolved minds and voices. In the meantime, we haven't been content to wait passively. We've started sending our own messages in a bottle, casting them into the cosmic sea. In 1972 and 1973, NASA launched the Pioneer 10 and 11 probes to the outer solar system, each carrying a metal plaque engraved with a picture of a man and woman and symbols showing Earth's location and our understanding of the galaxy. A snapshot of who sent these craft, in case some distant future finder can interpret it. Then in 1977 came the twin Voyagers, each equipped with the famous golden record. This phonograph record, plated in gold, contains a rich trove of Earth's sights and sounds, music from different cultures, from Bach to Chuck Berry, from Navajo chants to African drums, greetings spoken in dozens of human languages, the calls of whales and the chirping of birds, a mother's soothing words to her baby, the crackle of a fire and the laughter of children, even the brainwaves of a young woman in love. There are encoded photographs of our planet's landscapes, our DNA structure, and human life. It is a time capsule of Earth as it was in the 20th century, hurtling into interstellar space. The Voyagers have now left our solar system and entered the space between the stars. In about 40,000 years, Voyager 1 will drift within a couple of light years of another star, carrying its greeting from a long-vanished world. Whether any beings ever find it, we cannot know. But just the act of sending it is a testament to our hope and optimism. A brave, poetic gesture of outreach in a mostly silent sky. We have also beamed messages directly at the stars. In 1974, scientists used the Arecibo radio telescope in Puerto Rico to transmit a powerful signal toward a distant star cluster called M13. That message, a sequence of binary code lasting only 3 minutes, was designed to convey basic information about humanity and our planet. Our base 10 numbers, the structure of the DNA double helix, a crude image of a human figure, our location in the solar system. It was largely a symbolic event, as M13 is 25,000 light-years away. If anyone is there to receive it, we won't know for 50,000 years at best. Nonetheless, it marked our entry into what some call the galactic conversation. Since then, there have been a few other deliberate signal attempts, and of course, our radio and TV broadcasts have been leaking into space for over a century, a growing sphere of earthly chatter, now about 100 light-years across. Perhaps one day, far in the future, another civilization will detect the faint tracings of a 20th century radio drama or a 21st century pop song and know that, at least for a while, we were here. So far, we remain listeners in a quiet auditorium, waiting for a cosmic response. The great silence teaches us something profound. It highlights the preciousness of the life we do know. If indeed we are alone, even in just our galaxy, then we carry an immense responsibility. The responsibility of being the universe's only known witnesses and caretakers of consciousness. On the other hand, if we are not alone, if others are out there, then what a grander stage we are part of, and how thrilling it will be when that veil is pierced. Either way, the question of whether we are alone has moved from the realm of myth, are there gods in the heavens, to a scientific quest. Are there others like us out there? It is a question that has broadened our perspective and led us to build instruments and dream up missions that would have astonished our ancestors. On clear nights, when we stare up at the star-strewn sky, that question, are we alone, quietly resonates in our minds. There's a kind of kinship in it. Perhaps somewhere, on a planet circling one of those stars, a being is looking back at the glow of our sun, wondering the same. The very loneliness that question implies has driven us to search more fervently. And just in the past few decades, an incredible thing has happened to reinvigorate our hope. We began finding planets beyond our solar system, thousands upon thousands of them. Once, other worlds were mere imagination. Now, they are data points in our catalogues, each one a real place out there in the cosmos. The night sky above is no longer just a collection of twinkling lights. It has become a vast garden of worlds, each orbiting its own distant sun. Our lonely planet is not as solitary as it seemed. It's one among a multitude. With that discovery, the ancient question, are we alone, enters a new phase. We are no longer guessing in the dark. We have places to look, places to go, at least in our dreams, and countless opportunities to find that long-awaited cosmic companionship. Our journey now turns to these new horizons, to the garden of worlds that has unfolded among the stars, and the search for life that those worlds entice us to pursue. For generations, other worlds were the stuff of story and speculation. But as the 20th century gave way to the 21st, humanity finally opened a real window into that hidden realm. In 1995, astronomers detected the first planet orbiting a sun-like star, and since then, we have confirmed over 5,000 exoplanets, and counting, in our galaxy. It was as if a blind was lifted from our eyes. Beyond our solar system, planets are everywhere. At first, the discoveries came slowly and were puzzling. Giant planets, heftier than Jupiter, but orbiting scorchingly close to their stars, whipping around in days. These hot Jupiters were nothing like the orderly solar system we knew, and they upended our theories of planet formation. But soon the floodgates opened. Using improved telescopes and clever detection methods, we began to find a menagerie of worlds. Gas giants, larger than our Jupiter, and tiny rocky spheres, smaller than Earth. Planets with 2 suns in their sky, and solitary worlds flying dark between the stars. Dense, hot super-Earths, hugging small stars, and frigid gas dwarfs orbiting far from their sun's warmth. We found planets that orbit pulsars, the dead husks of stars, surviving in the harsh aftermath of a supernova. We found others that are so light and puffy that they could float in water, were there a cosmic ocean large enough. It seems planets form wherever they can, in all manner of environments, and in configurations that often surprise us. The more we searched, the more we learned that our own solar system, with its neat division of small inner rocky planets and large outer gas giants, is just one of countless architectures nature can assemble. Now we know that planets are practically ubiquitous. Most stars we peer at have at least one planet, and many have whole families of them. Some stars boast systems with multiple terrestrial-sized planets packed in close orbits, like the star TRAPPIST-1, which has 7 Earth-sized worlds tightly circling a faint red sun. Other systems have planets in orbits that are stretched out or tilted in wild ways. There are super-Earths, bigger than our Earth, but smaller than Neptune, which are common out there, even though we have none here. There are mini-Neptunes and gas dwarfs, categories of planets we didn't even imagine before we found them. This cornucopia of worlds has expanded our perspective immeasurably. No longer do we look up at the stars and see just pinpoints of light. Now each one is a potential solar system, a sun with its own retinue of planets. That change is as profound in its way as the Copernican revolution. We've moved from thinking of our solar system as the blueprint for all others, to realizing that it's just one particular garden plot in a vast, varied landscape. And among those myriad planets, we naturally fix our attention on those that might be like home. Among this cosmic garden of planets, some reside in zones that make us lean forward with excitement, the habitable zones of their stars. This is the comfortable band around a star where a planet could have the right temperature for liquid water on its surface, not boiled away by too much heat, not locked in ice by too little. It's a simple criterion, but on Earth, water was the crucible of life, so it's the first thing we look for. We sometimes call these regions the Goldilocks zones, because the conditions are not too hot, not too cold, but potentially just right. And indeed, we have found a number of planets in these temperate orbits, sparking intense interest. One of the earliest was Kepler 186f, a planet only a bit larger than Earth, orbiting a dim red dwarf star in the constellation Cygnus. It gets about 1/3 the sunlight Earth does, placing it in the cooler outer part of its star's habitable zone, but it could be a world of twilight and mist, perhaps warmed by a thick atmosphere. Then there's the TRAPPIST-1 system. 7 Earth-sized planets around a tiny, cool star, not much larger than Jupiter. 3 of those planets lie in the star's habitable zone, and all 7 could plausibly harbour liquid water under the right conditions. Imagine an entire mini-system of potentially water-bearing worlds, packed closer to their little star than Mercury is to the Sun. If life can arise on one of them, could it spread to neighbours? Could there be a multi-planet dance of life in that single system? These questions were science fiction a few years ago. Now they're scientific speculation grounded in actual data. Even our nearest stellar neighbour offers intrigue. In 2016, astronomers confirmed a planet around Proxima Centauri, the closest star to our Sun, at just 4.2 light-years away. This planet, Proxima b, is roughly Earth mass and orbits within Proxima's habitable zone. The catch is that Proxima Centauri is a red dwarf, much smaller and cooler than the Sun, so its habitable zone is very close in. Proxima b orbits its star in just 11 Earth days. Such a tight orbit likely means the planet is tidally locked, with one side perpetually facing the star, the other in constant night. What would it be like there? Perhaps the day side is a baked desert under the red glow of Proxima, while the night side is frigid and dark. But along the line between day and night, the terminator, maybe there could be a twilight band with milder conditions, where winds circulate warmth and allow clouds and rain. It's all conjecture for now. But remarkably, these are conjectures we may test in the future. Proxima b is close enough that upcoming telescopes might be able to probe its atmosphere for hints of water or even signs of life. The thought that the nearest star to us has a potentially habitable planet is a profound one. The cosmic ocean might not be as empty as it first appeared. The challenge in detecting life on an exoplanet is enormous, akin to spotting a firefly next to a searchlight from thousands of miles away. But we're developing the tools to try. When a planet passes in front of its star, an event called a transit, a tiny fraction of the star's light filters through the planet's atmosphere, if it has one, on its way to us. By spreading that light into a spectrum, we can look for the fingerprints of molecules in the planet's air. Already, using the Hubble and now the James Webb Space Telescope, we've detected water vapor, methane, and other gases in the atmospheres of some giant exoplanets. These are the early baby steps of a new field, astrobiology at interstellar distances. The Holy Grail would be to find a combination of gases that strongly suggests life. For example, on Earth, our atmosphere has abundant oxygen from plant photosynthesis and methane from microbes and other sources, and those gases normally would destroy each other unless continuously produced by living processes. Seeing something similar on a rocky exoplanet, oxygen along with methane or perhaps other imbalance indicative gases, would be a thrilling clue that biology might be at work. We haven't seen such an unmistakable biosignature yet, but the mere fact that we can even search for it is astonishing. We're sniffing the air of planets around stars hundreds of light years away, detecting the faint chemical whispers that might betray alien life. As we comb this garden of worlds, we remain aware that life may not always broadcast itself in obvious ways. Earth has been lush with life for over 3 billion years, but for most of that time, no one beyond our planet could have easily noticed. It took more than 2 billion years for oxygen, a byproduct of cyanobacteria, to accumulate in our skies. Even today, a keen alien observer with a powerful telescope could conclude something strange is afoot on Earth by our atmospheric chemistry and perhaps by seasonal changes in colour. But they might not remotely imagine the complexity and diversity of life here, let alone things like cities and technology. Life could be common in the universe and still usually be microscopic, subtle, and hidden. It might lurk under the ice of far-off moons or in the clouds of gas giant planets, places where we might not detect it from light years away. It's humbling to recognize that even as we search, we could overlook life simply because it doesn't produce a dramatic signature, or it exists in a form we don't yet understand. We also remember that our search for company includes our own solar system. Mars shows tantalizing hints, chemical signatures in its soil, and occasional methane spikes in its thin air that keep the question of past or present life open. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, have subsurface oceans beneath their icy crusts and even erupt geysers of water into space. Could something swim in those dark alien seas, warmed by undersea vents? We don't know, but plans are underway to find out. In a sense, the search for life has become both macrocosmic and microcosmic. We scan distant galaxies for faint biosignatures, and we also examine grains of soil on Mars or plumes from Enceladus for tiny microbes. We are, in every sense, on the threshold of possibly one of the greatest discoveries, or perhaps the confirmation of a great solitude. Each new world we discover, each new piece of data, brings us a little closer to answering the ancient question of life's uniqueness. The excitement is palpable. Within a generation, we've gone from having no evidence of any planets outside our own system to knowing that the galaxy is teeming with them. We've identified dozens that are tantalizing candidates for Earth-like conditions, and many hundreds more that, while uninhabitable themselves, add to our understanding of how planetary systems work. It feels as though we are standing in a vast orchard at dawn, surrounded by trees laden with fruit we cannot yet reach. We suspect some of that fruit may be sweet, harbouring life, and some bitter, barren, but we can only sample by inference for now. The light is slowly brightening as our technology and techniques improve, allowing us to see more and more. We are patient gardeners and curious gourmets at once, willing to wait, but keen to taste the knowledge that is ripening out there. This burgeoning knowledge also transforms how we see ourselves. Earth was once thought singular, then merely one of a few planets in the Sun's family. Now it seems to be one of billions in the Milky Way's planetary archipelago. That could make us feel small, as if we are just one drop in a cosmic ocean. Yet knowing that there are many worlds also makes the existence of life here more profound. If life is rare, our drop might be one of the few that shimmer with bioluminescence in the dark ocean, all the more precious. If life is common, then we are part of a vast cosmic ecosystem, and that is wondrous in a different way. Either perspective urges us to cherish our world and also to continue exploring others. We've learned that planets come and go, stars light up and eventually fade. Nothing in the universe stays the same forever. By mapping exoplanets and studying their stars, we even see cosmic evolution in action. Young systems still in formation, mature systems in balance, and some stars nearing the end of their fuel, with their planets destined to either freeze or be engulfed. This dynamic view underscores that our own story, Earth's story, is part of a larger cosmic tale of birth, change, and eventual ending. Thinking of endings might seem premature when we're flush with so many new beginnings, new worlds discovered almost weekly. But the cosmic garden of stars and planets is not eternal. Eventually, like any garden, it will go quiet. The star-forming nebulae that continue to blossom new stars will thin out. The remaining stars will age and die. It will take an unimaginably long time, but there will come a last generation of suns and a last planet circling the last shining light. Already, our universe is past its very youthful phase. The rate of new star birth has declined from its peak billions of years ago. The universe is still fertile with light and life now, but it won't always be so. As we marvel at the abundance of worlds today, we also gain a deeper appreciation for this era we live in, a time when the cosmos is illuminated by countless stars. A day will come in the distant, distant future when that is no longer the case. And thus our journey must now consider a different horizon, the fate of the universe itself, and the epoch when the stars themselves begin to fade. It is time to leave the relative warmth of our cosmic daytime and venture into the far future, into the universe's final twilight, a destination as sobering as it is fascinating. Our journey now carries us trillions upon trillions of years into the future, to a time almost beyond comprehension, the sunset of the universe. Picture a night sky in that far epoch, if indeed there are any eyes left to see it. It would look very different from the sky we know. The familiar constellations would long have drifted apart as stars moved through the galaxy. Many of those stars would no longer shine at all. The Milky Way, which in our time is a majestic spiral brimming with stellar light, would be a much dimmer place. The big, youthful stars, the hot blue giants that burn their fuel quickly, would have flared, exploded as supernovas, and vanished billions upon billions of years earlier. The medium stars like our Sun, which live for tens of billions of years, would have swollen into red giants, then sloughed off their outer layers to become small, dense white dwarfs, fading like cooling coals. Over eons, even those white dwarfs, which start off as hot as the core of a star, would cool and dim, turning into black dwarfs, essentially cold, dark spheres of carbon and oxygen cinders in space. The smallest stars, the red dwarfs, have incredibly long lifespans, trillions of years, sipping on their nuclear fuel slowly. But time is relentless. After trillions of years, one by one, Even the last red dwarfs will exhaust their hydrogen. The universe, once filled with countless points of starlight, will go largely dark. As the cosmos ages and expands, the creation of new stars slows and eventually stops. In galaxies like our Milky Way, there is only so much gas to form stars. Right now, that gas is recycled through generations. Stars are born, live, die in supernovas, and spread enriched gas that helps form new stars. But over very long times, that gas gets locked away. Some of it is captured by dead stars or flung out of the galaxy. With fewer raw materials, star formation dwindles. In the distant future, there will be no new stars igniting, no fresh stellar nurseries lighting up nebulae. Galaxies will turn into cosmic retirement homes for the aging stars that remain. They'll be populated mostly by red and orange stars, since the short-lived blue ones will be long gone, and then by fading embers like white dwarfs and neutron stars, the collapsed remnants of massive stars. These remnants themselves carry poetic names. White dwarfs, glowing faintly with stored heat, and neutron stars, city-sized, ultra-dense spheres, some of which may shine briefly as pulsars, but even those pulses will slow and stop eventually. In that far future, the universe enters what some astronomers call the degenerate era. Degenerate, not in a moral sense, but because the dominant objects are degenerate matter, the peculiar state of matter in white dwarfs and neutron stars. Imagine the galaxy at that time. Most of the visible bright stars are gone. Here and there a red dwarf might still cast a feeble glow. The very smallest red dwarfs can last perhaps 10 trillion years or more, so a few could still be around if we're not quite at that mark. But as time marches on, even those guttering flames will wink out. What remains is mostly dark. Planets, now frozen if they're not already vaporized or fallen into their stars. Cold dwarf stars, black dwarf remnants, neutron stars, and black holes. The nights, once ablaze with 1 billion stars, would be as black as coal, punctuated only by the occasional spark of a distant supernova in some other galaxy, also extremely rare now, or maybe the ghostly glow of collisions between stellar remnants. As galaxies lose their starlight, they also drift farther from one another. You see, our universe has been expanding since the Big Bang, and that expansion is accelerating due to dark energy. In our present era, galaxies outside our local group are receding from us, the more distant ones moving away faster. In trillions of years, if dark energy remains constant, galaxies that are not gravitationally bound to us will have been carried so far that their light fades beyond detection. An observer in the far future, in our own galaxy, or whatever merger remnant exists then, might see no other galaxies at all. They could be alone in a seemingly endless void, all other island universes having slipped beyond the cosmic horizon. The cosmos will appear to consist of one's own dark galaxy and nothing else, a profoundly lonelier vista than anything we can imagine now. Eventually, even the collisions of remnants will cease. Once in a great while in those deep future times, 2 dead stars or black holes might merge, releasing a final burst of energy, a last fireworks show. But such events would be separated by millions or billions of years of darkness. Time, which we mark by change and events, will in a sense lose meaning when almost nothing happens. 1 million years might go by, and the only event could be a lone atom decaying or a solitary flicker of a dying pulsar. What remains in such a universe? Black holes, for one, especially the supermassive black holes that sit in galactic centers. They would be among the last significant energy sources. Occasionally, a stray star or gas cloud might fall into one, and it would devour that matter and flare up briefly with emitted light and X-rays as the matter is torn apart. But after a while, even black holes will run out of food. Then they too face an ultimate fate, according to Stephen Hawking's theory: Hawking radiation. Black holes aren't completely black. Quantum effects cause them to very slowly lose mass by emitting faint radiation. For a stellar mass black hole, this process is fantastically slow. It might take 10^67 years, that's the number 1 followed by 67 zeros, for it to evaporate. For the supermassive black holes that weigh billions of suns, the evaporation time is almost inconceivable, on the order of 1,000 years or more. But given mind-boggling expanses of time, even these monsters will eventually fizzle out, each one popping like an ultra-slow firework, releasing its last energy into the cold sea of space. If some theories are correct, even matter itself may not last forever. Protons, the building blocks of atoms, might very slowly decay into lighter particles, though we have not observed this and it remains speculative. If protons do decay with a half-life of, say, 10^4 years or so, a commonly discussed figure in certain grand unified theories, then given enough time, all the atoms in the universe would eventually fall apart. Solid matter would dissolve into a fine mist of fundamental particles and radiation. The final picture of the universe would then be not one of black holes and cinders, but of an extremely thin soup of particles, each isolated by almost unimaginable distances, perhaps occasionally zapped by the phantom of a photon from some ancient decay, all of it hovering just a hair above absolute zero temperature. This is often called the heat death of the universe, not because it's hot, it's extremely cold by then, but because it represents a state of maximum entropy, where useful energy is gone and no organized structures or processes can persist. Contemplating such a fate is melancholic and mind-bending. All the brilliance and splendor we see now, the glitter of the Milky Way, the glow of nebulae, the radiance of billions of galaxies, would be extinguished. The era of light, life, and organized complexity would be a distant memory in a cosmos grown old and quiet. In that final darkness, the universe achieves a kind of silent simplicity. Some have poetically likened it to the universe falling asleep, or the eternal night settling in. And yet, viewed another way, this slow fade-out is gentle and deeply natural. The story of the cosmos, from the Big Bang until that end, is like a grand cosmic day. It started with a fiery dawn, the Big Bang's afterglow, followed by the bright noon of stars and galaxies in full bloom, and will end with an extended evening of long shadows and fading embers, until night fully falls. Unlike some earlier cosmic theories that envisioned a violent end, such as a big crunch that would have the universe collapse back into a fiery rebirth, or a big rip that would tear even atoms apart if dark energy grew too strong. The heat death scenario is peaceful in its way. It's not an apocalypse in fire, but in frost, a gradual ebbing of energy. Will that truly be the end? We cannot be certain. Our understanding of physics is incomplete. Quantum theory and general relativity have yet to be reconciled in the conditions of black holes and the Big Bang. It's possible that new physics might alter this picture. Perhaps proton decay doesn't happen, and black holes find some new way to spawn fresh universes, as some speculative ideas suggest. Perhaps ours is one bubble in a froth of universes, and while our bubble thins out, others are being born elsewhere, carrying on an endless cycle of cosmic creation. These ideas are highly speculative and currently untestable, but they remind us that when we talk about the far future, we are dealing with huge uncertainties. For now, the best picture we have is the gradually dimming cosmos, heading toward an extremely quiet state. This vision, while somber, also casts our present moment in a profound light. We live in what could be considered the cosmic afternoon, perhaps even still the morning, of the universe. Stars are still plentiful, galaxies still dazzle, new worlds are still being born. Life exists at least on one planet, and maybe on many. We are alive at a time when the universe is full of grandeur and accessible to our investigations. In the far future, any beings, if they could survive at all, would find it much harder to learn about the cosmos, because so much would be dark and distant. It's as if we are in a golden age of cosmic knowability. We can see the universe's past in the faint glow of the cosmic microwave background. We can see billions of galaxies. We can piece together our history because the light is still reaching us. A trillion years hence, that background glow will have redshifted into near nothingness, and other galaxies will wink out of sight. Civilizations then, again, if any could survive so long or arise so late, would see an entirely different sky, possibly concluding they were alone in a dark, static universe, never suspecting the rich cosmos that once was. Realizing the impermanence of all we take for granted can imbue us with a kind of bittersweet gratitude. The stars will not always be there to guide and amaze, but they are here now, and so are we. We find ourselves in the universe's age of light, able to bask in the glow of countless suns and to study a cosmos filled with structure. Our existence coincides with this era, and not coincidentally, is enabled by it. We are made of elements synthesized in stars and dispersed at a time when new solar systems could form. In a sense, we come from the cosmos at its height of vitality. Knowing that even the universe has a life cycle makes our appreciation of the now even sharper. It urges us to relish the cosmic beauty around us, the brilliant tapestry that is ours to witness. This awareness of cosmic mortality also brings the conversation back to ourselves, to the meaning we derive from being part of this grand story. We who are made of stardust, living in the universe's springtime, can find meaning in simply being here to experience it. We are ephemeral. Individual lives flicker for mere decades, and our species has been around for only a cosmic eye blink. And yet, for the moment, we carry the flame of consciousness. In us, the universe that will eventually go dark is, right now, alight with thought and curiosity. That realization carries a quiet, profound significance. It suggests that even as the cosmic lights will one day fade, something precious is occurring now. The universe is partially awake through us, reflecting on itself. So, as we imagine those far distant times and the final twilight of creation, we return our focus to the present moment, to our own time under the stars. We recognize that we live at a time filled with light and wonder, and that we have the opportunity to seek answers and understand our world and beyond. Knowing what eventually awaits the universe does not cast us into despair. Rather, it highlights how special it is that we have light, life, and intelligence now. It becomes ever clearer that finding meaning is our task. The universe, vast as it is, has given rise to creatures who can extract meaning from its very existence. We are made of stardust, and now we ask, what will we do with that knowledge? How will it shape our lives and our sense of purpose? We are stardust, literally born from the furnaces of long-dead stars. This realization is one of the crowning jewels of modern astronomy and physics. Every atom of carbon in our cells, every atom of calcium in our bones and iron in our blood, was forged in a star that lived and died before our solar system formed. Those atoms journeyed through interstellar space, gathered in a nascent cloud that became our sun and planets, and eventually became part of Earth, and part of us. When we say we are children of the stars, it is not just a metaphor, it is the plain truth. The universe is our ancestor. Understanding this has changed us. It's as if all of humanity has gone through a profound shift in self-awareness, akin to an individual learning about their long-lost family history and finding it awe-inspiring. Such knowledge can deeply affect the way we see ourselves. We often walk through life feeling separate from nature, separate from our environment, certainly separate from the stars in the sky. But when we internalize that we came from those stars, that the atoms in our body have existed for billions of years and were once inside flaming suns and drifting cosmic clouds, the boundary between us and the universe begins to blur. We start to see that we are not in the universe so much as of the universe. As the astrophysicist Carl Sagan famously said, "We are a way for the cosmos to know itself. Our existence allows the universe to reflect on its wonders. We are participants in the cosmic story, not mere bystanders." This perspective can be profoundly comforting and empowering. It tells us that we belong here, that we are natural, that our presence is an outgrowth of the way the universe works. The stars are our kin. When you look up and see the Milky Way, it's not just a collection of foreign lights. In a very real way, that's our extended family. Those stars are made of the same elements we are, and we share a common origin in the Big Bang and the stellar alchemies that followed. Feeling this connection can ease the sense of isolation that sometimes comes with being a tiny individual on a tiny planet. However distant and aloof the cosmos might seem, it is in truth very close to us. We carry pieces of it in our flesh and blood. Beyond the physical connection lies the almost spiritual one. The idea that through conscious beings like us, the universe achieves self-awareness. For billions of years after the Big Bang, there was darkness and inanimate matter, but no thoughts or dreams, as far as we know. Now, at least on Earth, the cosmos thinks and feels through living entities. When we gaze at the night sky, the universe is effectively looking back at itself through our eyes. That concept can instill a sense of purpose. Perhaps one reason we're here, if one were to assign reason, is to bear witness to the universe's splendor and to try to understand it. In doing so, we add meaning to the cosmos. The stars by themselves are magnificent, but when a mind beholds them and finds them beautiful, a new level of significance emerges. It's interesting to note that as scientific as the stardust revelation is, it brings us in a sense full circle to ancient intuitions. Many spiritual traditions have taught that we are one with the universe, that we are made of the elements, that life and the cosmos are interconnected. Science has provided the literal evidence for those poetic notions. We are made of earth and air, of fire, stellar nuclear fire, and water. We are one with the oceans and the rocks and the stars. This realization does not diminish the magic of existence. If anything, it enhances it. The truth of our origins is more astonishing than any myth. We became aware beings through a chain of events that links the heart of a supernova to the beating of a human heart. When people truly absorb this, it often triggers a feeling of awe. Standing under a dark sky and contemplating our cosmic genealogy one can feel simultaneously insignificant and deeply significant. Insignificant because we are so small and our lifespan so brief compared to the cosmos. Significant because we are rare, as far as we know, and capable of appreciating all this grandeur. This blend of humility and elevated perspective is one of the gifts of astronomy. It teaches us cosmic humility, recognizing that we're not the center of everything, but also cosmic pride, or perhaps gratitude is a better word. Recognizing that we are privileged to be part of something so vast and wondrous. The stars continue to inspire us in ways that go beyond science or logic. There is a reason that nearly every culture has stories and songs about the stars. When we step away from our day-to-day concerns and spend a moment under the night sky, we tap into a very old, very human experience. The modern scientist scanning data from a space telescope isn't so different in that moment of discovery from the ancient poet gazing up at Orion and finding meaning there. In both cases, a dialogue is happening between the human mind and the cosmos. That dialogue has shaped our art, our philosophy, and our very sense of ourselves. Consider how the image of Earth from space, the famous blue marble photograph taken by Apollo astronauts, influenced an entire generation's worldview. For the first time, we saw our planet as a whole, a fragile, lovely sphere hanging in the void, with no national borders, no divisions, just one world. That singular perspective helped fuel the environmental movement and a sense of global unity, because it reminded us that we all share this one home. Likewise, the pale blue dot photograph taken by Voyager 1 from beyond Neptune, in which Earth appears as a tiny speck, underscored our smallness and the folly of our self-importance. Sagan's reflections on that image, noting that every person we know, every event in human history, happened on that mote of dust, has become a modern scripture of humility and humanism. These are examples of how cosmic perspective can shift our values and priorities. The overview effect reported by astronauts, that almost spiritual sense of the unity and preciousness of Earth, is another manifestation of meaning drawn from a cosmic vantage. It demonstrates that sometimes to understand ourselves, we must step outside ourselves, in this case literally, into space, and view things from a greater distance. The stars and planets provide that vantage, even if only figuratively for most of us. When we internalize the cosmic perspective, it can encourage us to be kinder to one another and gentler with our planet. We see ourselves as one people traveling together through space and time, rather than as many separate factions. In this way, looking outward helps us look inward and improve. The sense of wonder we get from the cosmos can be akin to a spiritual feeling. It might not involve deities or scriptures, but it is an experience of profound awe and connection. When you lose yourself in contemplation of the stars, you may feel a transcendence of the self, a merging with something larger, feelings often described in religious contexts. It's not surprising that many people use words like soul-stirring or sacred when talking about a clear night under the Milky Way. That emotional response is part of finding meaning. It reminds us that factual knowledge alone, while powerful, isn't the whole story. It's our emotional and psychological relationship to that knowledge that shapes our sense of meaning. Knowing we are made of stardust is scientific, but feeling that we are part of the universe, that may be called spiritual or philosophical. Both aspects together enrich the human experience. In modern times, we might not attach literal religious significance to constellations as our ancestors did, but the stars still guide us. Not our ships or our planting schedules as much, but our aspirations and our curiosity. We build observatories on remote mountain peaks and launch telescopes into orbit, essentially because the stars call to something deep within us. The drive to explore and understand is a fundamental part of our humanity. In that sense, engaging with the cosmos is one way we express the yearning of the soul, using soul in the poetic sense of our inner self or spirit. The stars challenge us to learn, and in rising to that challenge, we have found not just facts, but inspiration. Science, rather than stripping away beauty, often reveals deeper layers of it. Knowing that the stars are nuclear furnaces doesn't make them less awesome. If anything, it adds a dimension of awe to realize that those tiny lights are gigantic suns, many times bigger than our own, and that some of those pinpoints are not single stars, but entire galaxies swirling with billions of stars. The reality of the universe, uncovered by our minds, has turned out to be more grand and strange than all the myths we once invented. We discovered black holes that warp space and time, and neutron stars that cram a sun's mass into a city's width. We found that space itself is expanding, carrying galaxies apart. We detected gravitational waves, ripples in the fabric of spacetime, from colliding black holes, affirming a phenomenon Einstein predicted a century ago. Each breakthrough is a testament to human ingenuity, and also another source of wonder. It's as if the more deeply we peer into creation, the more it rewards us with mind-boggling marvels. In finding meaning in the stars, we balance two modes of understanding, the analytical and the imaginative. We use telescopes, equations, and logic to decode what the stars are and how they work. But we also use metaphor, art, and introspection to understand what the stars mean to us personally. A person can stand under Orion and simultaneously know that Betelgeuse is a red supergiant star nearing the end of its life, and recall that in myth, Orion was a hunter slain by a scorpion and placed in the sky. These layers don't conflict, they complement. One speaks to our mind, the other to our heart. Together, they give a richer meaning than either alone. In that sense, our search for meaning in the cosmos is not a single-path journey, but a weaving of many strands, scientific, cultural, emotional. Ultimately, what meaning we find is a very personal matter. Some look at the immense universe and feel the presence of a creator or a divine plan, the fine-tuned physical constants, the emergence of consciousness. All this can reinforce their faith. Others look at the same facts and feel that life is all the more precious, precisely because it is a rare accident in a vast, indifferent cosmos. Meaning for them comes from cherishing the brief spark of awareness we have. Many find meaning simply in the search itself, in the joy of discovery, the satisfaction of figuring out a puzzle, the unity of working together as a global community to push the frontiers of knowledge. There is no single right answer, and that's the beauty of it. The universe provides the canvas. We supply the interpretation. Yet across these interpretations, common themes emerge: awe, connectedness, humility, curiosity, and a resolve to make our moments count. Standing here at the end of our exploration, figuratively under a canopy of stars once more, we can't help but circle back to those quietly twinkling lights and the questions they evoke in us. Why are we here? What is all this for? Humanity has asked these questions for as long as we have been able to think, and the stars have always been a mirror for them. The universe itself doesn't speak to tell us the answers. Its stars shine silently. Its galaxies spin in profound quiet. But in that silence, we often find that the act of questioning leads us to our own answers. Maybe we're here to appreciate the beauty around us and to make beauty of our own. Maybe we're here to connect with each other and find love and meaning together in the face of the cosmic vastness. Maybe we're here simply because the universe is such that life could emerge. And having emerged, we create purpose for ourselves. One thing is certain. As long as there are humans and a night sky, we will continue to seek meaning up there. We will project our hopes and fears onto the stars, and we will draw inspiration and courage from them. Our distant ancestors drew constellations and myths. We draw hypotheses and launch probes. But the impulse is the same. We are seekers by nature, and the infinite sky is the greatest canvas for our seeking. Our journey through the cosmos, from myths to knowledge, from creation to doom, from solitude to meaning, is a story still unfolding. We have by no means answered all our questions. In fact, we have as many as ever, if not more. The difference now is that our questions are sharper and deeper, informed by all we have learned. As we move into the final part of our reverie, we acknowledge those enduring mysteries, the quiet questions the universe has yet to answer. They are the whispers of eternity, subtle and persistent, that continue to call us to exploration. We have come so far, yet there is so much left to understand. And perhaps that is a good thing. Perhaps the endless mystery is itself part of the gift. Let us listen, then, to those whispers, the unanswered questions that beckon us onward, ensuring that our sense of wonder will never be exhausted. Even after all our centuries of stargazing, after all we have learned, the universe still holds vast mysteries close to its chest. In the quiet of a clear night, when we pause and let the enormity of it all wash over us, we can almost sense those unanswered questions echoing in the silence. One of the most profound is simply, how did it all begin? What brought the universe into existence? We have the Big Bang theory that describes how the universe expanded from an extremely hot, dense state roughly 13.8 billion years ago. We can trace the evolution from that initial fireball to the formation of atoms, stars, galaxies, and eventually us. But the Big Bang is silent on the cause. Why is there a universe at all, rather than nothing? What, if anything, happened before that moment? Was there a before, if time itself began then? These questions venture into territory where physics, philosophy, and even theology blur. Our equations break down at the very origin. They can't tell us why or what triggered the bang. Some modern theories speculate about quantum fluctuations or collisions of membranes in higher dimensions, spawning our cosmos. But these are hypotheses without evidence so far. The origin of the universe remains one of the greatest mysteries, the first whisper from the darkness that we strain to hear. Another enigma is the composition of the universe. Remarkably, the stars, planets, gas, dust, everything we can directly see, make up only about 5% of the total content of the cosmos. The rest is invisible to our eyes and instruments, inferred only by its gravitational effect on galaxies and galaxy clusters, or by the accelerating expansion of space. We call these unseen components dark matter and dark energy. But those names are really placeholders for our ignorance. Dark matter, making up about 27% of the universe, holds galaxies together with its gravity. Without it, the stars in the outer parts of galaxies would fly off, as the visible mass alone isn't enough to bind them. We've detected dark matter's influence since the 1970s, thanks to astronomers like Vera Rubin, who observed flat rotation curves of galaxies. Yet we still don't know what it actually is. Is it a new kind of particle? Maybe a WIMP, weakly interacting massive particle? Or something even more exotic like an axion? Billions of dark matter particles might be streaming through your body this very second without interacting with a single atom. Ghostly stuff that passes right through ordinary matter. Experiments deep underground and in particle accelerators are trying to catch a glimpse of dark matter, but so far it remains elusive. It's a humbling reminder that most of the matter in the universe is an unsolved puzzle. Then there's dark energy, even more baffling. In the late 1990s, two independent teams of astronomers observing distant supernovae discovered, to everyone's shock, that the expansion of the universe is not slowing down, as most expected it would due to gravity, but speeding up. Some force or energy intrinsic to space is pushing galaxies apart at an accelerating rate. We've named this mysterious phenomenon dark energy and estimated it makes up about 68% of the universe. But what is it? A property of the vacuum? A new field? An illusion caused by our misunderstanding of gravity at huge scales? We don't know. If it continues unabated, in many trillions of years, it will drive distant galaxies so far away that they become unreachable and unobservable, as we mused earlier. Dark energy is a whisper from the depths of spacetime, hinting that there's a layer of reality we have yet to grasp. It's as if the universe is composed mostly of an invisible fabric that we barely even knew was there. And now we're scrambling to understand it before it carries the cosmos beyond our sight. The mystery of life itself is also far from fully solved. We still seek to understand how life began on Earth. What sequence of chemistry sparked the leap from complex molecules to the first self-replicating living organisms? We have intriguing theories. Perhaps life's genesis was in a warm little pond, as Darwin speculated, or around hydrothermal vents deep in the primordial ocean. Or maybe it came from elsewhere, the panspermia idea. But we haven't pinpointed it. It's a difficult puzzle because it happened over 4 billion years ago and left scant direct evidence. Yet, answering it would illuminate whether life is likely to arise elsewhere. If it turns out that the origin of life is relatively easy under Earth-like conditions, then the universe might be teeming with microbes, even if intelligent life is rarer. If it's an exceedingly rare fluke, we might indeed be alone. We also don't fully understand consciousness, the very thing that allows us to contemplate all these mysteries. How do electrical impulses in neurons create subjective experience, the feeling of being you? This hard problem of consciousness is more philosophical, but intimately tied to life sciences and even physics, because it's asking whether our understanding of reality is missing something fundamental about the nature of mind. We wonder, too, about the ultimate fate of the universe, with a bit less than total certainty. Is the heat death absolutely certain, or could something intervene? Perhaps dark energy is not constant. Maybe it will eventually dissipate or change behavior, altering the fate of the cosmos. Some have imagined an oscillating universe, one that collapses and is reborn in a new Big Bang, the Big Bounce instead of heat death. While current evidence favours an endless expansion, the truth is we don't know for sure what a far future universe governed by physics we don't fully understand, dark energy, etc., will do. This is a realm where speculation meets the limits of inference, and we must be content with some uncertainty. We puzzle over questions that straddle the border of science and metaphysics. Are there other universes? Modern cosmological theories, such as eternal inflation or string theory's landscape, suggest that our Big Bang might not have been unique. There could be countless other bubble universes, each with their own laws of physics or constants, forever out of reach of one another. It's a heady concept, a multiverse, which if true would drastically expand the concept of reality. Yet, by definition, other universes, if they're truly separate, might be unobservable, making this more a matter of inference and philosophy than empirical science for now. Still, it's a question we can't help but ask. Is everything we see just a small part of an even grander, perhaps infinite, ensemble? If so, what does that mean for our search for meaning? It might mean that everything possible happens somewhere, which raises deep questions about probability and purpose. Even within our own universe, 95% of which is dark to us, there may be realms and phenomena we haven't even imagined. Physics is not finished. There could be entire aspects of the universe, hidden dimensions, new forces or particles, undiscovered principles, waiting to be found. Just a century ago, we didn't know that galaxies other than the Milky Way existed, or that space could expand, or that quantum mechanics allows particles to tunnel and entangle. What might the next centuries reveal if we are fortunate enough to continue learning? That question itself, what are we missing, is a whisper enticing us onward. One of the lovely truths about scientific discovery is that every answer tends to lead to new questions. We solved the riddle of the planetary motions, but that led to questions about gravity's nature. Newton answered some of that, which eventually led to questions about the nature of space and time themselves, which Einstein addressed, which raised questions about the quantum realm, and so on. The more the circle of light expands, the longer the perimeter of darkness around it becomes. Meaning, the more we know, the more we become aware of what we don't know. This can be seen not as a frustration, but as an invitation that will never expire. There will always be mysteries to inspire the next generation. Think of the young people now, who will be the astronomers, physicists, biologists of tomorrow. What astonishing questions will they answer? And what new puzzles will they uncover in turn? The quest for knowledge is unending, and therein lies much of its beauty. It ensures that humanity, if we survive and thrive, will never be bored, never run out of frontiers. Perhaps, too, there are limits to what we can know. There may be questions we cannot answer definitively, whether because of practical constraints, we can't build a particle accelerator as big as the solar system, say, which might be needed to probe certain energies, or cognitive ones. Perhaps some concepts are as hard for the human mind as quantum mechanics is for a dog, simply beyond intuitive grasp. Yet, even acknowledging that, we do not cease to try. The striving for understanding is part of who we are. It's worth remembering. In seeking these answers, we often find meaning in the search itself. We bond with each other through shared curiosity and collective effort. We create art and poetry inspired by the mysteries even before they're solved. The journey of inquiry enriches us, quite apart from the destination. Now, as our long journey through cosmic time and space comes to a close, we find ourselves once more under the canopy of the night sky, feeling both the weight and wonder of everything we've explored. We have travelled in our minds from the birth of the universe to its possible end, from the smallest atoms in our bodies to the grand structure of galaxies. We've gone from fireside myths to equations on blackboards to robots on Mars and probes beyond Pluto. We've asked questions that children ask and questions that only supercomputers can help answer. And through it all, the stars above have been our companions, constants that sparked our thoughts in the beginning and still spark them now. Reflecting on all of this, a kind of quiet reverence settles in. The universe is far vaster and more mysterious than our ancestors could have known. And yet, we have been able to touch some of those mysteries. We've decoded a bit of the cosmic DNA, so to speak. We've learned that we are part of this universe in every sense, physically, mentally, emotionally. The cosmic mystery and human curiosity are deeply intertwined. The more the universe challenges us with the unknown, the more our curiosity is provoked to respond. It's a conversation, one that's been going on since humans first looked up, and that will continue as long as humans exist to look and wonder. The riddles hidden among the stars, the ones we've solved and the many we haven't, have done more than teach us facts. They've taught us humility, when we learned we weren't the center of everything. Courage, to face vastness and not despair. And unity, when we saw Earth as a single pale blue dot. They've given us purpose, to learn, to explore, to protect our precious home, to maybe venture beyond it. In trying to answer them, we've built telescopes that peer back billions of years. We've invented mathematics that dances with the infinite. We've sent our machines to other worlds and our eyes to the edges of the visible universe. How remarkable a journey for a species that once huddled in caves fearing the night. As we conclude this reverie under the stars, it's clear that the story doesn't end here. In truth, the story of discovery and meaning never ends. We will carry on, each generation picking up where the last left off, adding its chapter to the grand saga. The universe will continue to whisper its quiet questions in the dark, and we, the curious children of the universe, will continue striving to answer. In doing so, we'll continue to find not only knowledge, but meaning, not only facts, but inspiration. So, let us take one last, lingering look at the sky above. The stars shine as they have for eons, each one a sun with its own secrets. The Milky Way arches overhead, a faint band made of uncountable stars, reminding us simultaneously of how small we are and how connected we are to this majestic cosmos. There is a peaceful finality in recognizing that it's okay not to have all the answers. The wonder we feel in the face of these cosmic questions is an answer. It's the universe awakening something within us, calling us to participate in its story. In the end, beneath the silent, gleaming sky, we find ourselves filled with gratitude. Gratitude for the chance to witness the universe, to study it, and to be a part of it. The cosmic mystery endures, and our curiosity endures. Our quiet search for meaning among the stars goes on, and as we each carry that search into our own lives, we remain, now and always, connected to the starlight above and the stardust within. The eternal night sky whispers, there is more to discover. And with hearts full of wonder, we gently whisper back, we will keep looking, we will keep listening. The dialogue between humanity and the cosmos continues, an endless story of mystery and hope, written in the language of light and the silence of the stars.